Okay, this next part is the kind of buckle your seatbelt part. As I try to offer a quick overview of what we've done over the last year. And for those of you who have been here before, and some of you many times before, I'll apologize for having some of the upfront material be repeated, but I think there are many new people always, and it's important for them to understand the context and the perspective. So I'll give a little background and history. Andy says, "Oh, you're not going to do that again?" And I said, "Andy, you've had to listen to it 22 times, but there are lots of people who don't know, and I think that background is important." So we started some time ago. Andy and Dijkstra, in the back there, were the very first pioneers there, helped dig the hole for a new building that was built. Not quite what we're in now, but where we are over there was a new building built specifically for the center in 1999. And when the rest of us, and I think there was a total of 12 at the time, got here in about January 2000, it was based on a small earmark, a $1.9 million earmark from Senator Gregg, who at that time was the chair of the Commerce Appropriations Committee. And earmarks are earmarks. I look at them as a seed that can be planted and grow into something nice, or it can just be something that's wasted. Or as somebody once said to me, our job was to turn pork into prosciutto. And hopefully that's what we've done. And I think that quickly became clear, because within 3 years, when we thought it would take like 5 years, we stopped being an earmark totally. We became a line item in the president's budget. That's a nice vote of confidence that we're doing something right. We expanded in terms of people, so we went from the first floor of the building where we all were to take over the second floor. And then by 2009, we got as far away from an earmark as you possibly can get, because there was we were authorized, not we at the University of New Hampshire, but the establishment of a joint hydrographic center was authorized on the PL 11111. We also in that year added a 10,000 square foot addition. You'll see when you go visit the visualization lab. And to me, that authorization was a great thing, because it's an acknowledgement on the part of the government that there's a need, and it also is a challenge because it becomes a competitive process at that time, which I think is a very healthy process. And so we had to compete, and we did in 2010 for the Joint Hydrographic Center, and we were awarded that a 5-year grant. We competed again in 2015 and were again awarded a 5-year grant. And then in 2017, we had yet another new addition. This room itself was part of that new addition. And on the other side, a whole number of offices for us upstairs. And on the bottom floor, which is really important, undergraduate labs that now are housing a good part of our new undergraduate Bachelor of Science in Ocean Engineering program, which I'll talk about in a minute, which is a very exciting new addition. Just a couple of years ago, it seems like yesterday, we competed again in 2020 and again won that competition. And so now we're operating on another 5-year award, 2020 to 2024. I think in your minds, in our mind, it's 2021 to 2025. We operate on a calendar year, but you guys operate a fiscal year. So Andy had me change the slide that says the grant is 2020 to 2024, but I don't want any of our people to get nervous. It actually goes on until 2025. And that's what we're reporting on now. It's our second year of that award. We have had since day one, and Ben remembers in 2002, the same slide, the same goals of the center: to be a world leader in the development of hydrographic and ocean mapping technologies and approaches, to expand the scope of ocean mapping clients and constituencies, to the development of innovative applications and collaborative work with both the private sector and government labs. And this really comes to what Ben was saying and Nicole was saying, that the work that you do as hydrographers, as ocean mappers, really serves many, many communities. And we've always believed that very much, and we've always tried to push NOAA and others into this broad range of applications for the collection of ocean mapping data, and for the use of the tools that you guys develop, which are really, really critical, again, in many other places. This idea of working with the private sector was kind of in our DNA from the very, very beginning. This has led to our industrial associates, and what you'll see tomorrow, and I don't know how we're going to fit them in the room, but we will try real hard to fit them in the room. If not, I said we'll move to another room. We'll have, I think we have 61 folks signed up. It's interesting, 61 associates. We don't have all the associates represented, just sending 2 or 3 people, but 61 folks signed up coming here. And it's been very, very exciting. Some of them very actively interact with us, some of them not. Just sign an agreement. We never hear from them again, but it's really, really useful for our students. And actually, I'll say something even to this group that I'll say to them tomorrow. We've actually had a problem with respect to students in that many of them are hiring our students before they graduate. And we've got to put a stop to that. It's not doing anybody any good. And I'll say that to our federal partners too. Please try not to hire them before they graduate. I know that they really look good and you want them to get working, but let us finish training them. Let us vet them in that sense too. So please, and I'll make that appeal to our industrial partners tomorrow too. But we also have, with respect to training, our educational component, I guess, was Nancy Foster, who won the Center Between Training, said, make baby hydrographers. We want to make baby hydrographers and ocean mappers. And we want to make grown-up ones too. And so we have our educational component. And again, you've heard the statistics, 2 undergraduates or so far. We have a really interesting model in that we're not an academic center, we're a research center. So we are not an academic department at the university. So our students have to come from an academic department, and we draw students from many, many different departments: ocean, electrical, mechanical engineering, earth sciences, computer sciences, oceanography, natural resources. We even, I think, have a zoologist or 2 around every once in a while. And that really makes for a really nice dynamic in there. It makes it difficult sometimes to teach because you're teaching students with very different backgrounds, but I think we've learned how to do that over the years. So we have both the master's and PhD program, graduate certificate program for those students who can't stay the full kind of 2.5, 3 years for a master's program. And the graduate certificate program also serves our JEBCO scholars, which I'll talk about in a minute. And we have non-degree programs offering short courses, seminars. We have undergraduate research fellowships, Holling scholars. And as I mentioned, we started a couple of years ago a Bachelor of Science in Ocean Engineering. And we're now having much more. At first, we really had nothing to do with undergraduates. Now we're having much more interaction with the undergraduates, bringing them into the program. And it's really, really paying off. We've had a FCE internship program that has really been successful. We've got great feedback from the folks at sea on NOAA ships, a couple of them. And we have a special undergraduate course being taught by one of our graduate students who really is doing a wonderful job for the undergraduates, and it's working. We've already had applications from some of these undergraduates into that program, one accepted and one will be accepted in the next year. So we're creating a cohort of students that can serve our program too. So we're very, very pleased about that undergraduate program. Sema, who leads our educational program, is constantly upgrading our courses. At your request, we've really made a switch from MATLAB focused in our to Python focused. I think there's a little internal debate, but we all agreed. And so we're really pushing the development of Python notebooks and things like that for a number of purposes, sometimes even to help the teachers in terms of grading and stuff. But Sem has also come up with a new linear algebra module, and each year it evolves. And again, having feedback from you folks who've been through the program has been very helpful in terms of evaluating the costs. The keynote of the program, the graduate program is a summer hydro course where the students are assigned the task. They've been asked to do a contract job. They have to plan it, mobilize it, do the acquisition of the data, do the survey, the processing, the reporting. They do that each year. This year they just finished it with challenges in COVID, but some have managed even through COVID. And this year we had pretty much a normal course, you'd say, not pretty much normal, not that constrained, but they pick an area that they survey, do usually a wonderful job. Sometimes the data added to the chart, sometimes not, almost always decons, dangers to navigation. I'll do that for or one non-hydrography. So it's really a wonderful experience. Yes, a wonderful experience. Yeah.
Very good experience.
So and again, okay. I mentioned the GEPCO program. This is something that started 19 years ago. It's quite remarkable. Roxy was a student in one of the early classes, now the director of the program. This has been just an amazing thing, funded by the Nippon Foundation, 6 students a year on average, coming from all over the world. I remember when we first started, this was the most international place on campus. It was really wonderful. It adds tremendous diversity to the tremendous food, new foods that we get introduced to. It's really great. This year's class, Azores, Denmark, Ireland, Japan, Sri Lanka. Next year's class, Tanzania, Kenya, Morocco, Oman, Ireland, Australia. They come for a year and little. The little is the extra hydrocrafts and their assignment that they go off on a ship somewhere. So if there's space on any ships you know of, they're always looking for that, or visiting a lab too. So they visit NCEI or labs in Sweden and things like that. And it's been tremendous, and they formed a phenomenal network and have been remarkably successful with that network. I think many of you know that a team of alumni won the $4 million Shell Ocean Discovery X Prize. That's a student. Usually I say that's buy a beer for everybody. But we've had 2 of our GEPCO students, graduates, represented their countries this year at the UN Global Geospatial Information Management Committee. On that committee, students from Kiribati and Jamaica. They have formed this really neat organization called Map the Gaps, which is serving the global mapping community, offering mappers for hire. It's really quite dynamic and wonderful. And they won yet another prize, which I can't yet, Roxy, I still can't discuss because it hasn't been announced yet. But next year you'll still get to know what that is. So really a tremendous community. We have what is it, 107 scholars to date from obviously all around the world, 45 countries. Talking about winning prizes, another team of UNH students and faculty, Christos there at the Canadian Hydrographic Conference, won the speed mapping challenge. And you'll hear more about that from Christos when he gives his presentation. Christos, who just, as I just flew in from Hawaii, he just flew in from Greece even more recently than I did. So he may even be more present. So as Marion mentioned, more than 200 graduates. The distribution here. This is who they are. I don't want you to read them all, but I want you to see the blue ones are folks who came to us from NOAA. And we have about 20 of those, and the whatever color that is, orangey type color, are students. And this is in a way I'm even more proud of, who didn't start working for NOAA but left here and went to work for NOAA. So we're hopefully a source for NOAA too. I don't think we had any that have gone to work for the Canadian Hydrographic Service. So maybe we should think about that. See if we can do that too. You hear all about the complementary centers, where the office, the Joint Hydrographic Center, that's what this is review about. This is a review of the Joint Hydrographic Center. That's the result of the cooperative agreement between NOAA and the university. And then you hear about the Center for Coastal and Ocean Mapping. And that's really something that sits at arm's length, the same people and everything. But for the Joint Hydrographic Center, what we're reviewing now, it's OCS, the Office Coast Survey, our primary sponsor. We also have support from OMAO, OAR through the Ocean Exploration Program, NGS Sanctuaries, NIMS, NCI. So it gets smaller and smaller as the support gets less and less. but so multiple parts to know. And we've always talked about, well, there's no question OCS is our prime customer. We try to serve all of NOAA and of course all of the country if we can. The Center for Coastal Ocean Mapping, CCOM, which we tend to call itself, again, same people, just putting a different hat on. That lets us stand at kind of arm's length to NOAA outside of the cooperative agreement, and it lets us make arrangements with other organizations, and so we can get funding from people outside of NOAA. And this year, about 6.3 million from non-NOAA sources. See the list of those sources there. We have had over the last few years tremendous cooperation with the Office of Exploration. Are you now Office of Exploration and Research, or just I get so confused. Is it
No.
OER?
Yeah, it can be.
That could be.
No,
then I don't-
no.
Oh, it's just like I exclude. I always say, is it I exclude or exclude? And I say, it could be either.
It could be. No ocean exploration.
No ocean exploration. Through a cooperative institute that we're part of with Woods Hole, USM, the Ocean Exploration Trust, and who did I leave out? URI. And this has been the mechanism through which we've acquired the DRIX, what we call DRIX 8. There's a number of DRIXs that you'll hear about. And this, again, is through the Cooperative Institute. And we have had a lot of field work this year. We have 3 cruises, March, shakedown cruise, which was our first time at sea, first time installing it on the Nautilus. We had a cruise in May, which was what we call a technology challenge, which was really, I think, a very successful cruise where we had the Nautilus, we had Woods Hole hybrid vehicle, the NUI, we had a Woods Hole midwater vehicle, Mesobot, and the DRIX, all operating in tandem, doing multiple vehicle operations with the DRIX as a surface vehicle, being the communications center. Roland's in the back here, sending commands to NUI, sending commands to Mesobot, tracking them all at the same time, keeping full situational awareness of all the vehicles. Well, the Nautilus could go off and do other work. So it was really wonderful. Sending all the information back to the ship, and that video, I should have looped it because I didn't realize I was going to talk so long about it. But we also were able to do something which I'm so excited about, which I call kind of directed verified sampling. We were able to tell the Mesobot that there was a target, the EK80, the sonar on the DRIX, saw a midwater target. It's important, this high amplitude midwater target. We told the Mesobot there's a target over there. We directed the Mesobot towards that target. And then we said the Mesobot has eDNA samplers on it. We sent the Mesobot to it. But more importantly, we saw precisely that it was there. We had no question. It wasn't blind. We could see the Mesobot exactly at the target. So when it sampled, we knew it was there. And I think this is going to open up a whole new world of kind of verified sampling. We don't have to sit there and guess, did we really get that target we're looking at? We can see what's going on because we could sit there and just move over the vehicle. So we're very, very excited about that effort. The other partnership we have, originally through a NOAA grant, but now evolving into, again, the Cooperative Institute support, is our work with the sail drone, the sail drone surveyor, the 73-foot or 72-foot sail-powered ASV. We did through NOAA the original testing of that, and the original sea acceptance trials, and then its first field test as it went from San Francisco to Hawaii, mapping all the way. Again, it includes a whole suite of environmental samplers on it. Now through the Cooperative Institute, through its funding, Sail Drone has just taken off, not just a few weeks ago, 3 weeks ago.
Almost a month ago.
Almost a month ago. Thank you. There's someone there. Thank you. Took off from Almeida, went up to Dutch Harbor. They did a little work on it in Dutch Harbor, and now it's out mapping areas for POEM, areas for OCS. Is the OCS area in there? And there are a number of deep water sites in there too, and data coming back. This is just last night.
They're in the OCS region right now. They're in the OCS region right now.
Great. Okay, so they're in the OCS region right now, and that's last night for you. So this is again a wonderful example of intra-NOAA cooperation. It's really nice to see. Okay, facilities here. I won't spend any time on you. Walk around, you'll see them. We have lots of nice facilities, particularly from a visualization and training perspective. Let's get to the grant and the new stuff. The way it works with the grant is there is a, now you have a new name for it. I keep calling it an FFO. It's a NOFO, Notice of Federal Funding Opportunity. Is that what I just call it Federal Funding Opportunity. I'm old, I can't change. And when that comes out, that's the call for proposals. And it prescribes at a certain level what it hopes the research lab will do. And there are, in the one that came out in the 2024 funding opportunity, there were 3 programmatic priorities. The First one, advanced technology map. That one had 3 components: data acquisition, data value, resources of the continental shelf. And these are not our words, that's the words of the FFO or NOPO. So we look at this as acquisition, collection of data, processing of data, and then continental shelf efforts. There's advanced technology for digital navigation services as the other programmatic priority, and the final one is the develop and advance marine geospatial and soundscape expertise. So those are defined. It also has another level of prescription in terms of what the proposal is looking for, and that is what we call research requirements. So those are basically a series of paragraphs that go into detail, and so there are 20 of those. And I'm just showing you one of them, just to give you an idea how it works. So for data acquisition under the advanced technology to map U.S. waters, improvement in the effectiveness, efficiency, and quality of acoustic and lidar bathymetry systems, backscatter, reflectance capabilities, vertical horizontal position orientation systems, other sensitive technologies for hydrographic surveying and ocean profiling. So that's the kind of thing we get. We get 20 of those type paragraphs that describe the things that NOAA is looking for in the proposal, and we then responded with 46 projects. And I don't expect you to read them here, but this is what they look like. You can see the PI of each one of them on there, and this is what we'll be reporting on now. Our progress in the second year, the kind of start of the second year of these 46 projects. I won't talk about all of them. I'll talk about only a few of them. I won't have any detail. It'll come a mile a minute. But we will have over the course of the morning and afternoon, I think about 8 or so, maybe 7. Remember, somebody will count more detailed presentations on some of it. But you'll certainly won't hear everything that's going on at the center. If you are more interested in what's going on in the center each year, at the end of the year, we produce quite a heavy annual report, 370 pages or so, and a lighter executive summary. We have copies of these. Brian has a whole pile of the executive summaries. We have copies of the full report. If anybody wants it, it's available on our website too. But if anybody wants to go home with the full volume, we have that there. So we reduced that. The last one, of course, is the one for 2021, and that's this one here. So that's what that is. So this will give you a much more, I can't say detailed, it's still just a cursory view, but at least it will touch on everything that's going on here, which I can't do in the next 30 minutes. So let's start. And I always say kind of buckle your seatbelts and see how we go. See, my voice holds out. We'll start. I'll try to go through in terms of the programmatic priorities, at least in that order. And the first one is really is advancing the technology to map U.S. waters and the data acquisition component of it. And this is really the largest one. You'll see I'll go on quite a while on here. Don't get nervous. The others get smaller and smaller because a lot of our efforts are focused on the collection and acquisition of data. We have in the tanks right next door a phenomenal facility that has evolved over the years for a state-of-the-art calibration facility. We can do routine measurements of a whole bunch of characteristics of sonars, and we use it all the time. We use it to calibrate our own sonars in the tank. We also use it to calibrate sonars for our industrial partners. And this year, despite COVID, we still were able to put a bunch of them through their tests. It's not a simple thing. It's like a 2-week process to really properly calibrate the sonar in the tank. But we did work for Meyer, Klein, MSI, and Combsburg. So that's in the tank. And again, we've worked on that. John Hughes Clarke. John, we'll talk much more about this. Whenever you see this, you know when and who's going to talk more about it. John and his students have been working on the other component of this. Well, we can calibrate things in the tank, but we can't bring every system in the tank. How do we start understanding how the systems are working, how they really work in the field, and how do we really get calibrated systems? Thank you very much, Brian. And so John will talk about his efforts and his students' effort to try to do sonar referenced vector beam patterns to compensate for the different amplitudes that we see through the different settings of the system, and very much improving, in this case, the backscatter, but also how we take that to sea and how you actually cross-calibrate. Small vessels are simple, but how do we do this with larger vessels? And we'll talk about a devious scheme he has, particularly sitting on the Canadian-US border, where each country can come without violating a law and survey looking at the same piece of seafloor. So we're fortunate to have neighbors like that. And you'll again hear more about that. Degrading our systems are a whole bunch of things. There's instrumental issues, but we also have a bunch of environmental issues. As we solve one, we kind of look to the next level of problem. And John will also talk about a range of environmental problems that they run into. Things like river plumes, freshwater, all kinds of sound speed issues. And John will go into detail about what they're doing in terms of trying to both visualize what's happening, but also trying to understand what's happening and its impact on the seafloor records you see, both from a bathymetric and a backscatter perspective. We've not only doing that with respect to the standard sonars you use. Tony Lyons in the back has been looking at the really high end of resolution in terms of synthetic aperture sonar and taking a look at the effect. First of all, the ability, it's both an ability and a problem that these sonars are responding to internal waves in the water column. But not only looking at the impact of those internal waves in terms of what we see from an image, but trying to really understand their effects and model those effects. And that's the key. And the question came up yesterday as we were talking about this, Tony, was, can they be corrected for? And I said the first step is modeling.
The CCOM funded student, Nicholas Amana, is working on this. He's getting a master's degree, hopefully in the fall. He's being lured away by industry. But the answer is yes. I would have liked him to stay and pursue that, but yeah. So you can use what you have there on the right to then re-beamform to get rid of the focusing defects.
And so from a target degradation perspective, we understand how it will be degraded now, and there's the hope that we can work through it. We have put a lot of effort into looking at the water column, the same sonars that you guys use for mapping and sometimes for fisheries world, for fisheries efforts. We found just a phenomenal amount of information about what's going on in the water column, which in turn affects what we see on the seafloor. Liz Widener, who wouldn't be here with us, but she's gone off to get married this week. Richard be with her. Someone, actually, Alex, her friend, is going to run from here to get to the wedding. Liz says, and I think I've talked about this in the past, we've been able to use broadband sonars to see phenomenal detail in the water column in terms of thermohaline steps, tracing the mixed layer for hundreds of kilometers acoustically, and even in the Baltic, taking a look at the hillicline and tracing that and mapping that over hundreds of kilometers. So very powerful ways to use the acoustics to see what's going on in the water column. What Liz and Tom are doing now is really taking a theoretical dive into this and trying to understand the nature of the stratification, building a theory to see how that transition takes place, with the hope that you can turn around and estimate the stratification intensity, do an inversion basically, and see what that stratification intensity is. So we really have a powerful tool to see what's going on in the water column from a temperature change perspective, salinity change perspective, and so on. And again, this all leads into better understanding of how it affects the seafloor. Turning that kind of theory into more practical and very pragmatic efforts, Alex and her thesis work took a look at a place called Platform Holly, which is a place that has a natural seep that's been going on for some time, and a platform standing right next to it. We're able to set up a sonar there, and Alex will talk to us in a few minutes about that in terms of the work they've done to look at both the discrimination of oil and gas and looking at flow rates. So we really can start drawing some very useful information out of it. The instruments themselves have problems, the environment causes problems, but I think for years, John has been singing this song. It's how we put them all together that really creates the issues, the integration. And so John has for a number of years been working on what we call the wobbles, how you get the wobbles out of the data we see. Brandon has taken over through his first master's and now PhD thesis with the RISC model, the rigorous intersensor calibrator, doing a least squared approach. Is that number here?
Number cruncher.
no, number cruncher approach.
Yeah.
To trying to really sort out the different variables that could potentially cause that problem. And now, last time we applied it, we showed you it applied to theoretical data or made up data, model data, now applied to real data and showing some improvement. And John will talk about that in his presentation. And then finally, once we put it all together, the question comes, as best we try to get rid of the environmental, the integration, the instrumentation problems. What is that limit of the resolution? How far can we push it? What kind of changes can we detect? Very fine scale changes can we detect in CCOM? And John, that'll be really the focus, I think, of John's presentation. Okay, we also try to develop tools that help us assess the performance of this, to come and help us as we're going along in the collection of data. And one of the most common, popular ones has been the Sound Speed Manager, which has been a wonderful example of collaboration between OCS and the lab with Giuseppe and colleagues at OCS. It's used by thousands, I think. Who knows the number here? 7,000 was 2,000, 3,000, 4,000.
Keep going.
Yeah, thousands of users worldwide. I don't remember exactly. But with each year, lots of changes and additions available in both Hydrographic to the NOAA internal process and Hydro. Paul, over here. Paul, thank you. Paul Johnson, working both through NSF funding and internal funding here. Not internal, but your funding, the JHC funding, through the MAC, Multibeam Advisory Committee from NSF, has been also providing a number of tools. We'll talk about some of them, but most importantly, I think, and most excitingly, this idea of a database of multibeam echo-sounder assessment sites and assessments. So you can, places where they've already staked out. There's a database you can go to and look for where you can do a patch test, an accuracy test, swatch performance tests, and so on. And with each one, documentation of line plans for doing that, settings, and so on. It's been a very, very useful resource. And even more exciting, I think, is this idea of establishing this wiki. Right word for it, a wiki? Yeah, an ocean mapping community wiki, and Paul will talk much more about that. Which really is collecting information. We just had this situation, Andy and I came back from seeing this week. And we have a problem with the 2040 when we were out there. And, Kongsberg right away says it's not their problem. It's so, and then, but being able to talk to people, other users, which we have an inside network, and find out, oh yes, this person had the same problem, that person had the same problem. It starts really building up the case for things being a real problem, not just one-off. And so this is going to be a very powerful. Is that okay? You guys just jump out if I say something wrong. We were very surprised, I have to say, in the NOFO to find that we were called to look at sub-bottom profiling systems. That's something we'd never been asked to do before. We were quite happy about it. Many of us have had lots of experience with them. So we didn't mind that at all. It was really kind of neat. And so it's in our plan. We have not been able to collect any sub-bottom data yet because we're still in the midst of the NEPA process for the sub-bottom work, which has been 2 years almost now. And so I think these things sometimes take time, but we've done a lot of preparatory work. We've looked at areas where we know we'll collect lots of nice data. We go to areas, we have areas picked out where we have lots of ground truth data. So we're quite ready as soon as the NEPA process is finished to start collecting data. We're not restricted, as you saw in the NOFO, to just sonar systems. It's all sources of entry. So our efforts are focused on LiDAR 2, and this is a collaboration with Chris Parrish at OSU, the creation of CBlue, the comprehensive bathymetric LiDAR uncertainty estimator. And this again a tool that's been widely used, accepted by industry, by the Corps of Engineers, and version 3 was just released 2 nights ago, 3 days ago, with a number of upgrades. So again, a tool that goes from a research creation to a really practical operational tool for creating both horizontal and vertical uncertainty for LiDAR data. Uncrewed systems. A huge effort of ours now over the last few years with respect to the JHC grant and with respect to our OECI efforts. We have a small fleet of ASVs. We started with the workhorse being the ASV, or excuse me, ASV, I should use ASV is the company. ASV Ben, we call it. We have some systems that have been donated, small systems to us. And then finally, the Dijkstra from OECI, OER. We have taken what we think is a very pragmatic and practical approach. Val, in the back, we'll talk much more about this, what we call practical autonomy. The idea that we want to operate obviously safely, effectively, efficiently, but for the purpose. So we don't lose track. We're not just doing waving arm theoretical stuff. We're remembering what our purpose is, collect hydrographic data, collect other data, whatever it is. We really try to keep focused on that purpose. I mentioned that the Dijkstra was purchased through the OECI grant, but we really had a tremendous opportunity on this last leg on the Nautilus to do in essence, a collaborative effort. The Nautilus was heading out to Papahanao, Mokuakea. Now I have to remember the rest of it. Marine National Monument. That's the part for me now. And was going to do deep water mapping for OECI, for OER. We hope to take advantage of that, the drifting on there, and seeing if we can do some OCS funding or JHC grant funded work that would help us learn its use for shallow water mapping from a charting perspective. And I think this is a really wonderful example of, again, intra-agency cooperation where we're really taking advantage of assets that we had. First of all, the lessons we learn, no matter who's funding the work, get shared to everybody. So NOAA, all across NOAA, we learn lessons. Val produces these wonderful reports about best practices. Every cruise we go on, we have lessons learned and things like that. And that's shared by everyone. So no matter who funds the cruise, who funds the instrument, everybody gains from the effort. Not only NOAA, but the broader community too. Because of course, everything we do is publicly available. And Val will talk more about that. With respect to the efforts that are funded by the JHC in terms of uncrewed vessel operation, we have a number of improvements to what we call Project 11, which is our software backbone for operating the systems, and Val will talk about that. Machine learning data for marine applications, this idea of developing a prototype sensor package for auto annotation of marine images, and again, Val will talk more about that. And path planning exercise. So a lot of software development rolling and students developing approaches to software architecture for path planning. And I didn't mention, but John will mention, I think, the work of the net. Yeah, so I mentioned that. I thought I would. One of our graduate students has been working with John to try to actually develop visualization, real-time visualization of the water column, but that's now being incorporated into the uncrewed level 2 as basically a machine learning ability to see what's going on in the water column for the tools. And again, Val will talk about that. I did want to take a few minutes. I said, Andy and I just got back from sea. Cruise had ended just a few days ago, where the center through OMAO and OCS funds funded 8 days of the Nautilus time of a much longer cruise, again, taking the opportunity of the ship being in the Marine National Monument. And our goals were really to understand the capabilities and limitations of Dijkstra as a shallow water mapping tool for charting purposes in remote areas. And that remote area we worked in was an island called Nahoa Island, which is about 150 miles west of Kauai, roughly, northwest. We had a large NOAA presence there. I have much more embarrassing pictures. Much more embarrassing. I restrained myself. We had obviously Lieutenant J.G. Early Pickett who's both a grad student with us, and came out on the cruise, and Lieutenant Mary Beth Head, who really was representing OMAO, is that appropriate? Yeah. So two NOAA Corps officers, Andy, of course, was there, and Don Jones, who's the technical lead for OMAO. Is that appropriate?
That's pretty close.
Pretty close, something like that. He talks a lot of good technology, and all of them took an absolutely active part in everything we did. But also saw what was good, saw what was bad. And we had a, this is the Drix team. So the NOAA folks and UNH folks on the Drix team. But even more amazing, on this cruise, we had, count them, 14, 12 official UNH people and 2 people contracted to, so two Frenchmen, right? So they feel very UNH-like. But we had 12 UNH people, many of them not with the Drix team. These are people that were contracted to the Nautilus as mappers or interns, JEPCO students as interns, graduate students who graduated working for OET. So it's really quite remarkable to have 12 UNH folks all on one cruise. Further goals we had were to develop protocols for dual vessel operations. How do you operate a mothership and can we operate as in parallel, run parallel surveys? There was LiDAR data collected around the HOA, and we wanted a junction with that LiDAR data. We also wanted to see if we can fill as many gaps as we could where the LiDAR went to extinction. There was some old multibeam data there that had been collected. We only got a grid from it that had been interpolated in a very funny way. There were very sparse lines of EM3000 collected on Hialakai. I think it was Hialakai, very sparse lines. So there was some multibeam data, but our priority areas were the gaps. We fill in the gaps. And wherever we could, we said if we could redo some of that sparse Hawaii compilation. We also were going to compare the mothership 30 kilohertz multibeam to the shallow water 2040 and see how useful that might be. It's not a combination that we would normally do, but the ship was there, so we said let it map too and see what that looked like. We learned a lot of things, and this is just a few days out. You'll get a much more detailed report as we think more about it. That's Nahoa Island. It's really a spectacular site. The Drix launches on a single pick on a crane, 4.5 tons. We had relatively rough weather most of the time. 20 knot winds on average, sometimes 30 knots, a few days down to 10 knots, but it was rough seas. The seas didn't diminish all that much. Launching a vehicle that large from a single pick is a tricky and dangerous thing. I think when you guys do it with davits, it'll still be tricky and dangerous, but it will be a little easier. There's no question. But I think we found, and I asked Andy and Mark Early, anybody else who's out there, I think that we were limited in terms of weather and sea state, in terms of launch and recovery. That was our big limitation. And it's likely similar to limits for a manned launch. I think the days we were able to launch, we could have launched a manned launch. The days we couldn't either. It'll be better with the Davit, I think, in terms of a little more agenda. But the key is once it Drix is in the water, it really has excellent sea capability. It doesn't matter. It doesn't mind that rough weather. It really works very well. And it can transit at very high speed. And that provided us an option that we really wouldn't have with manned vessels. And that's that we could, in one case, run all the way from the Nahoa, the 150 miles back to the lee of Niihau and Kauai, launch the vehicle there and then go running back and do a survey and still have enough endurance to do many hours of survey work. And then we only had to do that once, but we even had that option there, and we're able to, in other cases, just run behind the Nahoa, which doesn't have much of a lead, but we were able to run by there and then keep the vehicle in the water for days. And that's the real difference, I think, that we can steam to the lead, no violence, launch the vehicle and keep in the water for several days. Now we weren't, because of permitting reasons, able to survey at night. We can keep the vehicle in, but we couldn't survey at night because of the monument permitting restrictions. But had that restriction not be that, we could have certainly kept surveying overnight. I think we've learned also what the real endurance is, and it's probably on the order of 5-6 days at survey speed. So that gives you a lot of flexibility that you don't have with a manned system. And it really didn't matter how fast we went. the beauty of that wave piercing hull and the gondola is that the data is integrated with higher speed. We could survey at 10 knots. We use fuel a lot more quickly. So we try to optimize the speed for fuel, but certainly data quality never degraded no matter what speed we went. We had really no problem. It was a auto, was that your word? Auto? What did you say? Total. It was a total. Survey with the two vessels, the Nautilus, Trix, and we can do that with full telemetry, full situational awareness up to the range of broadband marine radio, which is about 20 kilometers on a good day, 15 kilometers on a bad day. It varies with atmospheric conditions, but we easily were able to run in parallel. We had deep water and shallow water operations, or shallow water and shallow water operations, depending on where we were. And at the end of the day, we filled in all the gaps. Certainly, we filled in some of the places where the multibeam data was. The tracks are where the Nautilus did, the others where the Dijkstra did. Had we been able to survey at night, I think we would have easily filled that whole box. And I'll turn to Airly, but I think you'd agree more than 95% of the data collected met or exceeded NOAA specs. What of that? Yeah, so the data was quality, and we did certainly achieve our goal of many junctions with the LiDAR, with the old multibeam data, and with the Nautilus multibeam data. So maybe the subject really speaks to all of this, maybe not. We'll see. We don't want to pressure her, but if everybody turns around and stares, that would be.
I'm easily pressured.
Okay, so I just want to update you on that. It's kind of just fresh off the press, so to speak. With respect to uncrewed vessels, we also have the visualization efforts, and Tom in the back, Tom Buckwitz, we'll talk more about that later today. But we're doing lots of cool stuff with 360-degree camera, which produces tremendously high resolution data. How do you transmit that over a broadband radio? The team has been working on ways to do what they call regional packing. You pick out the area of interest, and then magic. It gets it gets. What does it get done? What happens to it?
You get the stuff that you actually care about is sharper, and the stuff that you don't care about, like the sky, you just throw that away. Essentially,
that's not magic. Okay, but it works to get the important information you need back to you. Not only do we look at video data, LiDAR data, we also, as you saw in the FFO, have a mandate to look at volunteer data, and Brian will talk more about that later in terms of what they call the WIBL, wireless inexpensive data logger, and the idea of using, and this is a very cool idea, the reputation of the data and the data collector as a way to judge how valuable it would be and kind of to weight it in terms of its contribution to the final product. So Brian will go on more about that. When that flashes like that, we finally have turned to a new component. Now so that's the end of the collection. But again, don't get scared, because the collection is the acquisition is the dominant one. Data value. Brian will update us on where we've gone with cube and chart. Maybe you won't. Just a little. There's a machine learning component now in chart for LiDAR, and Brian will talk about cloud processing, something we're all interested in. And Brian's taking a very, very in-depth look at that, and our relationship to a NOAA effort in terms of cluster, and Eric's effort there, and that's been a real nice interaction too that we've had this opportunity to do. And again, you see cluster again here as we look at the work at Giuseppe in terms of the quality assurance tool, working very closely with Tian, Matt, and Julia. And again, these guys are constantly creating new toolkits for the QC tools that are kind of a daily use NOAA product. I knew all about it, but I'd never seen them in action until this cruise. When I watched Early do outlier checks and things like that, and so I saw how really nice they are. Satellite derived bathymetry, we've also been taking a look at. This is a collaborative work with Christos and Chris Parrish. I was looking for Chris Parrish's name up there. I didn't have it. I apologize. Chris Parrish and Christos and a student here. And this is an idea of actually accounting for the spatial heterogeneity of the sea bottom and the water clarity to improve the satellite derived bathymetry estimates and the accuracy. Because we know there's lots of variability. The more you can parse it, the more you can get an accurate estimate of seafloor depth. Excuse me. Also along those lines of satellite derived bathymetry, again, CCOM-JHC and OSU partnership, looking at best practices, testing the NOAA Bathy tool. Stop for a second. Oh, let that slide go. Oh, I think it's sorry. It's still very early in the morning for me, 6 hours early. It's 4:30 in the morning. We have also been taking a look at ISTAT data. I think we're all excited about the potential of ISTAT2. So Yuri and Tim Lowell have been looking at new algorithms, developing new algorithms to try to get us more accurate extraction of bathymetry from ISTAT2 data. That was called for in the FFO, and we're certainly pursuing that. We're also looking at other sources of data, and this comes back to a lot of what Nicole was talking about, that these data have all kinds of applications. So we're doing a lot of work with structure for motion, coral reef heads, but really pushing this in terms of the analysis with respect to trying to get out a quantitative estimate of the surface area, the rugosity. Most of that work is done in a kind of a general broad sense. What Jenn will talk about, Jenn and Tom working on this idea of a real 3D rugosity that's scale dependent. And it's really interesting that it's scale dependent. And Jenn will then talk about expanding this to a multi-scale, multi-resolution project that looks at these sorts of issues. We've now gone to the third component, resources of the continental shelf. This ties into a lot of the work we've done for the extended continental shelf. That is coming to an end, believe it or not, after 20 years, 43 task force meetings, 96 working group meetings, 19 executive committee meetings, 23 multi-day workshops, and I guarantee hundreds of more informal meetings that Andy and I have gone to. The lab has been responsible for collecting more than 3 million square kilometers of new multi-beam data that's all been made publicly available. We're working very closely with NCEI, Paul, to make sure that that data it's always been submitted, but we want to make sure that it's fully accessible through the National Archives. It's been probably one of the largest contributors to CBET 2030, and it's leading now, which I hope will be its legacy, to many value-added products. We've seen examples of that. Sour's work. One of our graduates who got off to work for NOAA. Derek, you're here. Welcome back. He just came back from Q2. Where Derek has looked at our entire mapping of the Atlantic and characterized it by geoforms, its morphology, through tools we've developed here, a tool called BREST, and it's come up with a quite nice, consistent, and reproducible habitat classification scheme. Looking at a finer scale, they were also able to see cold water corals in one area of that data set, and found the largest continuous cold water coral mountain province yet discovered. Is that still true?
Yes, it is.
Good. It's not a lie. The same application of BREST, this seafloor characterization package, has been now applied. Larry Ward, is Larry here? No. Larry, to the national bathymetric source on Gulf of Maine bathymetry, and it's come up with a landform and geoform package, which has been part of a Office of Coastal Management. Is that OC?
Yeah, Office of Coastal Management,
Yeah,
and in conjunction with the states.
Yeah, with a project on creating a Gulf of Maine seascape. So the tools that we've developed here, again, put into practical application. And again, I think coming back to Nicole's comments and Ben's comments of that, serving a much broader purpose than we necessarily think of. And this comes back to what I mentioned before with Jenn and Chris Parrish, again, looking at multi-resolution, multi-scale resource mapping, starting at satellite scale, coming down to the optical scale. And Jenn will talk more about that. a little later today. We've gone to the next, finally, to the next programmatic priority, and again, we'll get much quicker now, I promise. And this is advancing digital navigation. And really, this is all about digital and computed aided cartography, visualization and manipulation of hydrographic and ocean mapping data. Work led by Christos. Brian is involved in that too, and the Viz Lab, a nice collaboration. And there are lots and lots of projects here and lots of collaborators. And I'm just going to read their names. Christos will not talk about all 11 or 12 of these, but a subset of them to give you more detail. But again, anything that kind of strikes your fancy, if you're interested, we just find Christos after Thursday afternoon, and we'll be available to talk more about it or look in the reports. Questions? I'll probably take 5 more minutes. This comes back up.
I never give presentations in case you haven't noticed.
Great, thank you. That was quick. Thank you very much. Okay, and so yeah, I was just going to hydrographic sounding selection, data quality, polygon simplification, sounding selection validation toward automatic chart production, cartographic sounding selection, survey to CATSOC, which is guidelines for allocation of CATSOC values for survey data, development of symbology. And you'll see that I think Tom will talk a little more about some of the symbology that Christos developed and its application. Performing cross checks of EQ chapters of existing X100 product specifications, prototype cartographic production using open and free software. This is the challenge, the CHC challenge. And Christos will talk in more depth about that. So again, all these going on in questions, if you're interested in any of those, just talk to Christos. And finally, something that we've been working on for a long time, which is visualizing uncertainty. It's a real challenge to all of us, and this we take advantage of our Viz Lab. We take advantage of our cartographic, our digital cartographic expertise, and that combination, I think, is making some progress. And you'll talk about that one. Okay. And just to give you an example of how that works, Colin Ware, who is the former director of our Viz Lab, still an adjunct with us, he's kind of a visualization theorist, and he actually has a degree in psychology and used to cut the eyes out of cats and things like that. So, to understand, sorry, to understand perception. It's not with us anymore, so it's okay. That's why he retired. Okay, so he's been looking at the theory of perception and trying to understand how we can create optimal color maps for shaded surfaces, something that we do all the time, but really kind of degrade the data doing that. And that's each one of our visualization tools kind of gains from those kinds of theoretical looks. We also have been trying to serve data in new and innovative ways, and Paul has been developing new tools and new approaches for serving large data sets. He'll talk more about our portal in terms of the tools we offer. And particularly exciting has been some tools that Paul has developed that allow us to do collaborative editing of data sets around the world. This is really focused on CETA 2030. When folks find problems in the data set, they can come in and just annotate those, and then it goes, everybody can look at that problem and try to resolve it. So Paul will talk more about that. With respect to precise navigation, we've had a large effort. Tom will talk a lot about that. There are many levels to that. Web-based 3D visualization of the next generation S100 data sets. Streamlines have been a particularly interesting one where we've not, as we zoom in and into data sets, the standard streamline is not capable of giving the resolution. I will demonstrate that to you. But they've come up with an approach that can generate much higher resolution streamlines for web serving. They have developed all kinds of ways to integrate LiDAR data. And I'll show you a wonderful data set from the Mississippi River integrate S11 surface current data and a bunch of other prototype S100 data sets integrated with OCS ECDIS data pulled from the display service. At least it didn't go up. But we also been pulling stuff from Coast Pilot. Brianna has been working on approaches to actually pulling things from text sources, and this combination of LiDAR and that text source becomes a very, very powerful tool for seeing what's going on. And this is best seen by Tom's demo. I think Tom will show that later today. And in the course of that, because they've been handling so much LiDAR data comes in no matter what happens to it before, very messy. And so they've developed a very, very powerful VR tool with kind of egg beaters that can go and really clean the virtual, clean the LiDAR data set very, very quickly. And Tom will show a video of that here, but also you probably best see in real life. Also, in looking at new approaches to looking at data, and then emphasize how do we get data to people. The VizLab and Tom have been looking at the role of augmented reality. There are many people using augmented reality. They tend to use just a single camera feed, a fixed camera view. And the question that they've been looking at is that good enough as opposed to really a true heads-up display, and have created this just phenomenal simulator in the lab. You'll all get a chance to see this. And I've been to some of the multi-million-dollar simulators, grid simulators, and this is just a few $1,000s of hardware here, and a lot of real smarts to put it together. And you can do all kinds of really useful experiments here. And so again, Tom will show you that, and you'll have the opportunity, if you haven't seen it, to come to the Viz Lab and take a look at that. We even have a little model of our own bridge and the wheel and things like that. Finally, our last programmatic priority: develop an advanced marine geospatial and soundscape expertise. This is really focused on our efforts to understand just what multibeam sonars are putting into the water column and what the potential impact of that may be on the very serious issue that we take seriously. I've reported in the past, and Jenn has reported, Jenn Mixus-Olds, or the work of her and Stephen Hillary at the SCORE array, where we have made measurements with many hydrophones on the seafloor, hydrophones that can listen to resident population of Cuvier-beaked whales, very sensitive whale species. And so the Navy tracks them all the time. This is the place where the Navy demonstrated that their sonars had a significant impact on the beaked whales. They actually left the range for several days after Navy exercises. And so we were able to come and repeat that kind of experiment, actually repeated it exactly, with multibeam sonar, with 12 kilohertz multibeam sonar. And there have now been 3 papers, I think, Jenn, 3 papers are published?
3 or 4, yeah.
Yeah, 3 or 4 papers that talk all about that. And I think, and I'll say it in my words, Jenn, you say it in the proper words. I think with respect to the metric that's used for looking at impact in these studies, which is the feeding behavior of the Cuvier-beaked whales, we've seen no real measurable impact.
Can we say my words?
Yeah, sure. I wanted to be honest.
I would say during the time of the multi-beam surveys, both temporally and spatially, the animals stayed on the range and continued to feed.
Okay.
That's the bottom line.
Yep. Okay. Well, they're quite different than the behavior with the Navy sonars.
Opposite, yes.
Okay, that's fair enough. But part of that same study is Mike Smith, who's really been trying to look at what the sonar is putting out. And he'll talk to us later today about their efforts to really, based on what they measured through the hydrophones at the array, look at the radiation patterns of multibeam. And from a modeling perspective, he'll talk to us about a meeting that he just came back from, where for the first time, the people who are kind of feeding into the regulators are now starting to look at multibeam from a modeling perspective, as opposed to just trying to take an air gun and make it into a multibeam. Mike will talk about that. Finally, we clearly recognize that outreach is critical. We have a very active outreach effort, Tara, leading the charge on people, and Colleen on the website. So we have all the social media things. It doesn't mean much to me because I'm very bad at social media stuff, but we have the appropriate social media presence, I think, and followers. We have a wonderful seminar series, which I think one part of the COVID experience has led us to make those much more available virtually, and I think we'll continue to do that. All seminars will always be virtually available now. So we'll have speakers in person, and we have those recorded on video. And the nicest thing is that we've started to have visitors again, and we can go to conferences again. That's part of our outreach effort. And one of the most exciting ones are sea perch efforts, which Tara heads up around here. We've always hosted the Seacoast Sea Perch. I think we had our first one in person again recently, but even more exciting in 2023, thanks to OECI, and the challenge will be sponsored by OER and organized by Tara here. This is the international challenge. So we're very proud of that and look forward to that. This is good. 2 days ago, picture. Val, you take the picture?
I did take that picture.
Val took that picture, and to me, it summed it all up. It was raining, I guess, that day. Andy and John from NOAA kind of shows hopefully the cooperation and the collaboration we've had, and hopefully that will continue. And I apologize, I've gone on 10 minutes too long. I'll blame it on my voice. And we'll make up for it because it's the break time now. It is break time.
Yes, it is.
So again, everybody will be available on Thursday afternoon if you have any more questions, and you'll hear a lot more in depth about some of the things, but things that I talked about. Okay, we come back at.
It says 11.
Let's come back at 11:05. Okay, 11:05.
Okay, so as Larry mentioned, a subset of us are going to give a little more detail and presentation on that massive list of 46 tasks that we work on. But the hope is to give you an idea in a specific subset of some of the work we're doing. So I'm going to be starting off with my title. I actually have to apologize on the bus this morning. I read it again. Why your measurements are never as good as you typically. I'm meant to be much more useful about that. And I apologize, pronouns are very selective these days. What I'm actually going to talk about is my measurements and why I'm always screwing them up. And so that's the real situation here, is that what we're trying to do, OCS collects fabulous data, but there's always issues with it. And we want to understand that better. And that's part of our role here, is to dig into that. There's a group of us, there's a number of tasks, there's a group of faculty that are involved. And actually, as you'll see with the backscatter aspects, we're very lucky to work with HSTV, Harper, and actually Becky Martinelich from N7, the engineering branch of NAMO. And when I say measurements, I'm talking about both bathymetry and, to address many more of these non-traditional issues, backscatter. But what the real superpower we have here is actually our graduate students. I'm going to be presenting their work under these 4 tasks that we're going to talk about. There's 5 current and there's 2 just starting here. And I'll be actually showing you their work. It's good to know that as well as the funding we received through OCS, actually the majority of students here are externally funded, and that really is complementary. So the tasks, the numbers, there's 3 of them in white are the problems. Integration, calibration of backscatter, and the fact that the environment is always changing, the sound speed. And the 4th is the one that excites me, that's change detection. That's the opportunity to address a number of these issues is as the seabed changes, and it does in response to climate, human interaction, or just naturally. And that change I'm referring to is both bathymetry and backscatter. So we've had these parallel programs going on both coasts. The one on the west coast is actually externally supported, but the vessel you'll see tomorrow evening, the RBGS, and we've actually apply this continuously, and these are the measurements that I've been corrupting. And I want to understand why. It's very frustrating. And so all of the problems, integration, calibration, and monitoring impact our ability to see the seabed breathe, literally move by decimeters. And it's actually very important thing about sort of offshore wind farms, scour around them, very practical application as we go forward. And this is something we're doing repetitively, both on the East Coast. You're looking at the wind speeds and the Isle of Shoals, which drive the offshore sediment transport. This is after today, this is our reporting period. COVID sort of went away. UNH had this fabulous strategy, and we were back operational by midsummer of last year. But particularly this year, and on the West Coast, we're really looking at the Fraser River. It's one of the biggest survey challenges, and this is just the discharge of the Fraser. So with these programs, there are a variety of problems. So the first task is integration. We've all had sea floors that look wobbly, and it's frustrating. And we have these beautiful stabilized systems responding to these periodic undulations, to the surface wave activity. They're great till they go wrong. When they go wrong, they go terribly wrong. And this is what Brandon has been focusing on for the last, well, actually, he started off modeling it all theoretically, but in the last 2 years, he's taken real data and basically tried to extract that out. And he's generally been very successful with it. But we want a test bed. We want a seafloor that's benign. That is, it's kind of smooth and boring. And then we're going to wreck it and see if he can fix it. And so we needed a test bed. And so what we did is the local test bed is actually just offshore here. We're just around the corner up in Durham. That's Fort Point, where the RBGS is, flatbreads, recommendation for supper tonight. And we're very lucky to have this seafloor. It's so convenient to us, but it's New England, it's bedrock everywhere, which is rough. But it's this smooth sand sheet that's just 20 minutes off the dock that is very, very active. Although it looks the same every year, it has been beat up by the northeasters and it's been ripped by the tides. It's a dynamically stable seabed. It looks the same, but it is shifting all the time. And because of long legacy we have, 20 years of hydrocamps, we know an awful lot about it and the sediment distribution. The bedrock's all high backscatter, but it's this low backscatter zone that goes round to the beaches of Rye. And we're looking for this mobile sands, and I actually wanted a gradation in backscatter. So the target area we picked, I actually wanted a transition, and this gentle mound in sediment is actually moving. And so that's where our focus site is, and it's very quick to get to. It's only 20 minutes away, and it's got all the requirements. And the reason it's so mobile is we're very exposed here. So you have all these Atlantic storms or the nor'easters coming down from Fundy, and it's remobilizing that sediment. We don't go to sea during the storms, but we can nip round the corner just 6 to 12 hours later and be in high motion, but not dangerous. Skip will make sure it's not dangerous. And we can test the data. It's no challenge in a flat calm. But when you have motion, things can go wrong. And this was Brandon's challenge. We took a corridor through this almost featureless seabed, and it doesn't matter. You can steam into the swell, with the swell, across the swell. You can generate pitch, roll, all the spectrums and collect data. We really push it plus or minus 72 degrees. And when it works really well. Lobster pots for scale. But he can disrupt it. And when I say disrupt it, he just moves the lever arms by a couple of decimeters or shoves in a few 5 or 10 milliseconds of latency. And the question is, can he fix it? And that was his challenge. If you subtract it from the truth, you see this wobbling. But just to remind you, special order is there. What he's introduced is that. We are still in spec. And that's the real impressive thing is, can you do that? And not one error. Everyone can solve one. But when you've got 5 or 6 or more, the norm, can you do that? So he's got very good at this. And if you had listened to his CHC presentation a couple of months ago now, he's able to solve this through awfully clever number crunching, which is incredibly computer intensive. It's cheap now. And so he's generally been very good. And he has this integration engine. It's really these 3 parameters that he's trying to solve for simultaneously. And he's actually very good at it with the ones that are invariant. A little bit of lever arms, a little bit of alignment, a little bit of latency, no problem, because it's there all the time. What he's never been able to handle is if the sound speed. He needs give him 30 minutes to an hour's worth of data and he'll solve it. But if the sound speed's changing in 5 minutes, he can't. He's just converging it, keeps on failing to converge. And so that's the sound speed issue. So that moves to the second problem. that's environment. And we all know that the biggest driver of sound speed, apart from solar heating, is freshwater input. So where to go? For the last couple of years, I've been working in the mouth of the Fraser and actually the Squamish on the west coast. It's a serious river. But on the east coast, if we want to be more local, you'll notice there's no major rivers classed by that number scale on the east coast. It's basically a line source. If you come up here, the only serious river in the Gulf of Maine is the St. John. And if we come down to us here in the Piscataqua, excuse me, that's not a river. I was very dismissive of this, and I found the problem. There's no oceanographic problems here, and I was completely wrong. As it turns out, people know an awful lot about this, and they haven't been focusing here. They've been focusing up in Great Bay here. We're very lucky to have two modelers that have been working the last 5 years. Salme Cook's got a model. It's forced from offshore, but it's trying to look in here. And similarly today, more recently, Jenn is working on a model. It's actually for a tidal power station that's on the bridge downtown. And again, looking at that. That one's barotropic, but this one's baroclinic. So you can actually see the sound speed effects from that. So if we look at the area we're interested in, which is the river mouth, you can see what's going on. And Salme's model was showing us that there's this jet on the ebb tide, and we're down here. So it is going to influence us. We're not far enough offshore. Even though it's a small, pathetic river, it turns out the tidal excursions are extremely important. And Jann's model, though, is frightening. And Indra, actually, the chap who's working on this, he's actually taken the model, made it finer, and closed up on the boundary condition. That's salinity. But notice the scale. It's only 0.2 parts per thousand. Why should that matter? As it turns out, the water that goes in and out of the Great Bay has hugely different thermal. It goes in there in the summer and it gets cooked. It goes in there in the winter, it gets chilled. So when we're operating here, this was why Brandon couldn't converge. So to give you an idea, we all nowadays have a surface sound speed probe. These are the 5 surveys. And as we start the survey, we build our way through, we keep on finding abrupt changes in sound speed. And I've got to emphasize, this isn't minor, this is 14 meters a second. So it's not like that 1 to 2 meters a second, maybe I should do a dip. And that is 11 minutes. So this is the challenge. And so many of our coastal areas have exactly this problem. To give you an idea what this does to the data, well, what do they look like? Often you can't see them. Actually, the majority of the time you can't see them. But when you do, they're there. But it turns out water column imaging is actually a very effective way of picking up the tidal front. And you see it, this is the offshore water, high turbulence at the front, and then the lower boundary is actually undulating. You can't really tell it there anymore, but you can see the front, and we're imaging all the time. So this is a grid, not a bathymetric. I figured it out. This is just the sound speed in 8 hours, doing this line 40 times. And you'll notice on the offshore side, it's a very, very stable sound speed. That's the front, and then you've got these massive undulations in sound speed as well there. So let's just take a couple of those lines, just step through them and see what's happening in 11 minutes. So the top is just the sound speed, and the scale there, that's 15 meters a second range. There's the tidal front. All of a sudden it jumps. You can see it in the water column imaging. That's the seabed there. If you look very closely, you can see how much heave we're doing. I would send Brandon and Miguel out. I wouldn't go. There's a lot of motion. It doesn't matter if you're in homogeneous water, how much you do that. As soon as you get into a stratified water mass, that really affects it. Notice the sound speed undulations. They're plus or minus a meter a second in 20 seconds. So it's really frustrating, and you can look at the data, one line, the next, and just watch the tidal front move through our data. And what actually happens is in the bathymetry, you're very stable. When you hit the front, all of a sudden you're unstable and you lose your ability to do target detection. Again, lobster pulse scale. So this is the challenge. And so Indra is working both in trying to image it and also to model it as well, to see if we could actually predict the front, which I don't think we'll ever quite do. But we want this display in real time. And that leads to one of the other graduate students that actually Larry mentioned, and that was Lynette. So everybody's got the real-time displays. But I wish the pie diagram is useless, quite frankly. You can't see anything in there because it's an instantaneous and it's replaced. But what she did is she wanted to reproduce these time series where we can clearly see the turbulence in the water. And she built, over a matter of 18 months, a real-time viewer that just sits on the machine right next to you, and you have a real-time scrolling display. It's qualitative because you can't always see them, the event. Just as every hydrographer looks at the clouds, looks at the sea surface, you should be looking at the scattering environment. So let's move to the third project, and that is backscatter calibration. So bathymetry has problems, environmental and integration. But backscatter, which is kind of the great white hope here, is has always been disappointing because of lack of calibration. No two launches or vessels give you the same number. Nobody really knows what they're measuring. Well, actually, there's a group that really do know, and that's, Alex will be talking about. There's a group here that I was very lucky to become part of, 7 years ago when I arrived, that really look into calibration of these systems. Why do we do it? Well, presidential memorandum, that's that one word characterizing, but let's think, why are we really doing it? Turns out Fish and Wildlife and NOAA have always had habitat mandates. Look in Canada, Environment Canada is legislated to monitor all the offshore disposal sites, and they're doing that with backscatter. And Fisheries and Oceans, the ancient Fisheries Act, you must not do a HAD, which is a harmful alteration and destruction of habitat. And so as we see a lot of these changing coastal environments, we want to be able to monitor that over regional scales. So how do you measure absolute backscatter strength? Well, you can with these amazing split beam fisheries systems, and you see Alex talk about this in the next presentation. You don't think of this as a hydrographic tool, but it's a calibration tool, and we need them. So we're clumsily suspending one, and we're sweeping through a range of frequencies from 40 kilohertz, 400 kilohertz. And we just mechanically rotated. This was 2 years ago, and we did this in the Gulf Islands regions in Canada. And what we've done this year is we moved that to the border, and we've actually moved it to Puget Sound, where many of the NOAA platforms were based, but they still go through there. So it's all very well to get the truth, but now you have to take your multibeam, which is a multi-sector stabilized system, and you have to break it up. And this is Miguel's thesis that he'll be defending in about a month's time. And so you had to give a different calibration for the first and the second swath. He had to allow for the transmit beam patterns for the first and the second swath, all sonar reference. And then uniquely, when you have this yaw stabilization, it's great for target detection, but notice that the received sensitivity, it's varying. He did that. So I encourage you, hopefully we'll Zoom broadcast that as well in about a month's time. But that's 2 steps. But it's not very practical at the moment. We've done this in shallow water up in the Canadian Gulf Islands, and it's not a practical place to bring in a larger platform. Unfortunately, these have lower frequency sonars. They want the seabed to be further away. It's too shallow there, and you have to be to do the calibration. So we needed to move that into a deeper water area that would be more suitable for major platforms. It was actually built around the Fairweather, which has just been upgraded to a 712. She was going to do a relative trial against some of the public NAVO data. And then she was on her way to Alaska, and the hope was she would be nipping through the inside passage. Other things intervened. The Fairweather, I don't think ever made it, but she will. And the Fairweather, I think, is coming back. And so what we did is we actually had to avoid the shipping lanes, practically. And so what we also did is took our 712 on a little 10-meter launch, calibrated it there, so it's in theory golden, and brought it and resurveyed a zone here. And as Larry mentioned, you don't have to cross any borders here. You just be part of ship's length on one side and not really notice. And the corridor is 400 meters wide. So come in here without offense to Victoria traffic or Seattle traffic, and you should be able to do this. So I'm not sure this is ready for prime time, but this is the method we believe is practical. But that actually ignores a whole other bunch. In fact, the majority of the sonar systems operate in OCS. It's the launches. I think there's about 8 of them on the West Coast, on the Fairweather and the Rainier. And actually, NOAA are well ahead of this. Shelley Devereux, from about 2017 onwards, the boats used to be, the vessels, the ships, sorry, used to be in Lake Washington, and all the launches would just do all their pre-season tests just here in Shoal Bay, and they would actually all survey the same piece of the sea floor. It wasn't an absolute backscatter calibration, it was relative. They actually ended up moving it over to Port Madison just because there's a lot of freshwater problems there. But and with Harper's help, I was able to get hold of all that old data and actually compare all the systems. But in the last 2 years, NOAA are actually doing the same thing. They have 10 of these 34-foot vessels with, again, 2040s on them. And we're able to take all of those and run them over. We ended up not using these areas for reasons I could explain without more time, but we actually went to here. But all of these are now relative calibrations. We can bring them all up to a common reference. We've just got no idea what it is. So again, the part of this year's program, they were very kindly have made us available one of those launches. We'll just finish first with the problem. So this is the Rainier launches, 1, 2, 3. So you think each one you calibrate them. Remember, each method has 2 swaths. They're different for the first and the second. And then the pulse length is, so I've actually shown you only 8 of the available pulse frequency combinations. It's actually 11. So you have to do that 11 times for each launch. And so it ends up being a massive data management cross-calibration exercise. But even if you've pegged it, you don't know what you've pegged it to. But fortunately, and this is just last week, and again, Harper was involved with this as well. This is one of the NAVO launches. It's exactly the same EK systems. And we actually went to the Shoal site to tie in the earlier surveys, those ones for the 19 and 20, and this for the 21, 22 data. And so the hope is, and this still needs work, but is we be able to cross-calibrate to an absolute reference all the backscatter measurements made by most of the federal platforms. And that, I think, is what we want to move towards if we want to look at backscatter change. So the last thing is let's apply all of this. Seabed change detection. I once was a marine geologist and I love it, but it's really frustrating. I want to see the seabed move. I want to see active seabed transport. And I want to see it both bathymetrically, but also want to know if the substrate is changing. So that's the challenge. It's obvious when a sand wave moves because they're huge. But imagine an expansive sand sheet. Is it accreting or deflating at this sort of scale? And as it gets a little bit coarser and a little bit finer, that's the sort of thing you see with climate change. Just as everyone says, oh, 1 degree by 2050. Well, it's going to matter, all of this. So this is the surveys we've been doing of that flat area off Portsmouth. We've done it in November, January, March, May, and just a few weeks ago. And it is incredibly smooth. There's some bedrock for reference and some boulders as well. And of course, we've got the backscatter measurements for all of these. Does it change bathymetrically with the seasons? Does it change in substrate type during the seasons? That's what we would like to know. And it's a habitat as well. It's also a lobster fishing area. So bathymetric, let's just take a couple of the surveys, January, March, and May, and subtract one from the other. And this is the difference map. And you go, God, that's awful. It's just a mess. That's not geological. That's the 2 survey patterns. But bear in mind the scale that I've got this at, plus or minus 25 centimeters. So what you see is all sorts of ship trap parallel bias, and this is primarily the sound speed issue that coping with. But take off your glasses and you'll notice that that's brighter there between those 2 and darker there between those 2. And I may be influenced and biased, but I actually think the seabed is growing in the spring as the red remains of the storms have moved it up to the crest of that ridge. And by the summer, it's starting to shift away. And of course, I could be dreaming, but that's the challenge. I want to see that plus or minus 10 centimeters. So let's focus in. Why do I think this sheet is moving? Well, look at the surveys. This is now a 25 centimeter resolution. See the boulders, they hopefully don't move. But notice the boundary between the 2. This is a thin sand sheet. It's about 30 to 40 centimeters thick on the edge. And you can see that boundary is migrating. You can see the underlying platform is appearing and disappearing. You can also see that it's featureless, except for the lobster pots. And what you see is when they put a lobster pot down, within about a week, the scour forms around it. After they take it up, after about 10 days, the hole is still there, and it takes time. You can actually see the effects. So the lobster pots are actually showing us that that's mobile. So I want to see that move. If I do a difference map, I can always see the edges. It's very obvious that it's changing at the edges. What I'm really interested in is this regional sheet here. And unfortunately, the main thing you see is ship track parallel. So its sound speed remains, honestly, I think one of our worst problems. Wobbles, we've actually got a good handle on the ones that are systematic. But bear in mind, all these surveys, this is the total difference between them. It's special order. They're actually all special order surveys, but I don't think they're good enough yet for what we want to do. And we need to understand not every place has these river plume problems. And that river plume problem doesn't always affect us. Depends on the time of the year. On a neap tide, it's much less as well. So the backscatter is the last factor here. That's one survey, that's the other. And I've deliberately not suppressed the angular response. So, of course, we're doing orthogonal surveys. What you're actually seeing here is the backscatter strength as it varies with grazing angles. Sometimes it's a broad crest. Sometimes it's very sharp. Notice how that gets sharp, becomes diffuse. At low grazing angles, there's no difference. And in the gravels, there really is no angular response. So you can't really compare backscatter in the same way. All the software you use hides this. And you don't realize it's doing it. And so now you subtract the two, but it never hides it perfectly because it's doing a rolling estimator. And so you've got these kind of halos flowing out. But let's try and subtract those two surfaces. That's before the angular response, that's after cosmetically removing it. And let's subtract them. I've just enhanced it a little bit. So one minus the other. And so this is plus or minus 10 dB. Do you notice this one, the difference? It seems to be getting darker between there and there. Do I believe it? And then brighter. And you can actually quantify it. So we're looking at a couple of dB when you average over, half a square kilometer there. And is that real? And to be honest, I would rarely ever believe that. We're fortunate we use exactly the same instrumentation as long as I got the attenuation coefficient right. In the high backscatter areas, it's reduced. But it turns out there's a separate project that's actually been looking at this for the last year and a half. It's actually led by Tony Lyons there at the back, ONR funded. And he's taken those same calibrated systems and left them on the seabed for months. And what he's shown, and this is only a tiny subset of his work, is the surface just goes backwards and forwards, driven by storms and other things we may not understand, as much as 5 and maybe more dB. So this is a natural thing we have to be aware of. And that's actually Khan's going to be starting on that. So I'll finish. This is by no means a completed program, but wobbles we're getting closer to. Oceanography, we have to understand it and avoid it, is my view. Not bad, it's not bad. It's this backscatter. I think we have to really get serious in this backscatter calibration. We have a couple of theses, but there's a lot of data management we haven't got right. The work that Khan's going to be doing, I'm mainly under Tony's supervision, and Indra's going to be working on modeling of the river plume, and actually Daniel's going to be looking at all that backscatter changes. So I'll finish at that, but I hope it's a flavor of what the graduate students are doing here.
Yesterday, they clapped when John gave us our Nobel Prize.
Hello, everyone. Good morning. My name is Alexandra Padilla. Today, I'll be presenting some of the work that comprises of my thesis. I'm a recent graduate student here at the center. And my work focuses under task 7, water column mapping. In particular, I'll be talking about our efforts in trying to monitor oil and gas in the water column. And so kind of a brief review on why are we interested in understanding methane release or hydrocarbon release in the ocean is because this becomes a very important environmental impact within the water column or in the atmosphere itself. These natural hydrocarbon plumes are emitted across the ocean seafloor and undergo a very complicated journey through the water column In the case of methane bubbles, that gas gets stripped, gets into the water column, and in shallow waters can potentially leak into the atmosphere. And so my thesis compromises of two ideas. The first one is how do we improve our capacity to quantify methane flux and transport through the water column? And this is mostly trying to look at how we do acoustic inversion techniques or dissolution models. And one of the first topics of my thesis, we look at how different bubble shapes and sizes affect our acoustic scattering models and how we can use that to better interpret our acoustic inversion techniques. In the second one, we look at how different shapes and sizes of bubbles, as well as surface coatings, such as hydrates, as we can see here in the image, affect our interpretation of physical properties such as rise velocity and mass transfer coefficient. And so these two chapters really give us an idea of how we can use models to better interpret our quantification of methane flux through the water column. The second idea is to improve our capacity for long-term monitoring of methane flux through the seafloor. And so that's going to be the talk for the rest of this session. So I'm going to take you to a known seep site off of the coast of Santa Barbara, California. This is known as the Coal Oil Point seep field. It is known for its prolific natural hydrocarbon activity, and with reason. So these are some video images and just some photography of the natural hydrocarbon seepage in this region. This is a very shallow site, it's about 70-meter water depth. So a lot of the oil and the gas is reaching the upper part of the water column and seeping into the atmosphere. And so in 2006, and one of the important things that this site is really known for is that a lot of people have gone to research it and really tried to interpret how environmental influences such as tides or storms, as well as oil production, can affect the release of methane within the site. And so in 2016, we went out as a group in collaboration with the University of California, Santa Barbara, to go and acoustically map this site. And we also took a device to help do some direct quantification of gas flux in the water column so that we can combine both our acoustic and our direct measurements to obtain this map that shows the distribution of methane flux through the water column. In particular, we're going to focus on a region known as Platform Holly. In this region, there is a large activity of natural seepage, and this provided the opportunity for us to attach an acoustic system and do some long-term monitoring of this natural seep. And so what we did is we took a split beam echo sounder, we mounted it on one of the support rigs on the oil platform. The transducer itself is positioned at a 15-degree declination angle, and this allows us to see the seafloor. And also, we were able to use this pen and tilt system to actually map the spatial extent of the plume just west of the platform itself. So the transducer that we use is a split beam echo sounder, similar to the ones that John presented in his presentation. And what this transducer really allows us to do is to track the position of the targets within the acoustic beam of the transducer itself. It allows us to calibrate our acoustic measurements, which provides a lot of important data sets. And so I'm going to talk about two data sets that we collected. This is with the pen and tilt system. We're able to pen and tilt through the entire plume just west of the platform. We have the seafloor just about out of 150 meters away from the center point. And we can see this plume that extends just to the west. And we can see both the spatial and temporal variability and the intensity and the position of these plumes. And we collected this kind of data set from September 2019 to October 2019. But due to some malfunctions with the pen and tilt system itself, we had to fix the transducer just to face towards a westward direction. And this is what that looks like here. Even in this fixed position, we're able to track the spatial and temporal variability of the intensity of the plumes itself. And so with this fixed position, we collected data from about November 2019 to December 2020. We have the seafloor again at about 150 meters. And within the water column itself, between 0 and 150, we see this plume that is changing. It's migrating in space, but also changing in intensity. And so we have this big data set, and what we're trying to do is really try to quantify the methane flux into in the water column and also potentially into the atmosphere. However, this is all just acoustic data, and it's all relative. So how can we convert this acoustic data into an actual measurement of gas flux? And usually what we do is we have a direct instrument that can collect direct measurements of gas flow. We can calibrate that to our acoustic measurements. However, due to COVID, we weren't able to go back out to the site to do these direct measurements. And so we had to be creative in how we can actually go and take these measurements just using the acoustic data set itself to get some sort of idea of what the changes are. And so what we did is we took a look at a small subset of the data. So again, so this is our acoustic data from just a couple of days of the survey itself. And because of the split beam capability of the transducer, we're able to look at the positions of the targets within the acoustic beam of the transducer. And so we have the alongship and the athwarship angles. And here I have a diagram just to help you visualize what that means. We have the alongship, which is basically the vertical position of the bubble, where we have the athwarship is the horizontal positions. And so if we look at the angle data from the targets itself of the plume, we can start to see some structure in the angle data. And so if we just highlight a couple of those. So the first one being, where in one direction we have this very structured, coherent angle. We have this ramp in the phase angle of the target itself, while in the other position, the other angle, it's fairly constant. And the way that we can observe that, if we can imagine it, is just single gas bubbles rising through that acoustic beam of the transducer. So just a discrete bubble column. Now, if we look at a different region in our data set, we have, in one direction, we have an incoherent angle structure, while we still have some constant angles in the other direction. And you can imagine this to be a stream of bubble screens coming up in a particular direction within the acoustic beam of the transducer. And finally, we have the case where in both directions, we have an incoherent angle for the bubbles itself, with the targets. And what that looks like in the acoustic beam is just a cloud of bubbles. And this is actually a video of gas bubbles within that region itself. And so what this provides us is information that can, within the angle data itself of the beam transducer, can help us identify different plume structures. However, we have about a year and a half worth of data, so we really want to do this in a very simple way. And so what we ended up doing is looking at a parameter that's known as the coherence factor. So this helps us identify when targets are coherent. So a target that's coherent is very localized within that acoustic beam. And a target that's incoherent, it's diffused within that acoustic beam. And so using this parameter, we can then look at the coherence in both the vertical and the horizontal directions. And if we compare that to a threshold where there's no gas bubbles, we can start to identify different plume structures by looking at both of the coherence in both directions. And what this provides us is with a set of different types of identifications of bubble columns, screens, and clouds within our acoustic data itself. So we can take the acoustic record and intensities and convert that into a classification scheme. And this allows us to derive a lot of information about how the plume structures are changing in time within the acoustic beam. But what this ultimately allows us to do is to identify the different plume classifications that then we can use different types of equations to then back out gas flux. And that's kind of what I'm going to talk about here. So for the different types, we have discrete columns, screens, and clouds. Each of those are going to have a unique way that we represent our gas flow measurement. So I'm going to start with a discrete bubble column because that's the simplest. So we have this N term. So that's just the number of bubbles within a unit height. And that is multiplied by this term here. So this really describes the volume of gas bubbles within a unit height that we're interested in. So we have the volume of the bubble. We have the rise velocity of the bubble, UZ. That's how fast they're rising. We have some external velocities that might be through currents or just upwelling of the bubble columns themselves. And also the bubble size distribution. So this is what tells us the size distribution of bubbles within the area that we're looking at. And so this equation here provides the gas flow rate of bubbles within that unit height. And if we're going to look at screens or diffuse clouds, we have to add the spatial extent. So that's how far they extend either in the lateral or in the aerial extent of those bubble size. So these are the equations that tell us gas flow rates. However, we also, because we're using acoustics, we have an equation that's very similar that tells us how the acoustic scattering cross-section is a function of the different types of plume structures, as well as the average backscattering cross-section of these bubbles. And so between these two sets of equations, one that focuses on the acoustics and one that focuses on the gas flow rates, the one commonality is this N term, which is the number of bubbles that we're observing within our data, within the beam of the transducer. And if that's constant between both, we can take those equations and lump them into each other. So now we have a direct path to go from acoustic measurements into gas flow estimates, just using acoustic data sets itself. However, one of the things that's really important is that we have information about the bubble size distribution of the plume itself. If we don't have that information, we can still provide some normalized estimate of the gas flow rate. So that's what this QASD means. It's the normalized gas flow rate that is dependent on the acoustic scattering and also the spatial distribution of the plumes itself, while we can separate that out from the physical properties of the gas bubbles. And so what I'll be reporting, because in platform poly there isn't any bubble size distribution that's currently known, I can still present the normalized gas flow rates that can provide some additional information. And so now what that means is that we can compare the estimates of gas flow rates for each of these different types of plumes. And so what that looks like, this is again the swath. So this was done between September and October of 2019. Here we have a time series of what that normalized gas flow is over that month of data. And what we can see is that within just a couple of days of the data that we collected, we can see changes in the normalized gas flow rates that are within an order of magnitude. Even then, within a day, we can see changes of the gas flow rates are within an order of magnitude itself. So we're seeing these very drastic changes in the gas flow rates that are caused by temporal variations due to external physical processes such as tides and atmospheric pressure. And so we can look at the time series that can help, this power spectral density that will help us identify some of those important periods that are probably affecting this change. And so we can see peaks in the 24, 12, and 8 hours, which are related to tides, but also atmospheric changes, pressure. For the long-term time series, it's important to recognize that, again, this is with that fixed view. So we're only seeing a small portion of the plume itself, but the black line is just the data that we collected, the raw data, which is every 10 seconds. And then the red line is daily averages of that data set. And then the oranges, the green dots are the monthly averages. And as we can see, even though we're just capturing a small portion, we can see temporal variation and spatial variation of the plume itself. However, if you look at the monthly changes, it's pretty much constant throughout the course of the year. And if we looked again at the power spectral density function, we can see again 24 and 12-hour peaks. Again, it's most likely caused by the tidal and atmospheric conditions within the site itself. And so just to summarize, what we've been able to do here is to use just acoustic measurements to be able to identify different plume structures, to then go and take that into a measurement that we can use to compare our gas flow measurements over the course of the year. However, if we had some understanding of what the bubble size distribution was, we can go back and calculate the actual gas flux rate. And one of the things that I found out really later on in my dissertation was that there was a study done in 1999. They don't actually measure the bubble size distribution itself, but what they do say is that they observe a range of bubble sizes from 1 to 15 millimeters with the mean size of 6 millimeters. And if we were to just create our own bubble size distribution using a Rayleigh distribution, we can start to begin to model this term here that will give us an estimate of what that that actual gas flow rate is. And so from my thesis from the other two chapters, we're able to use a specific rise velocity model developed by McGinnis et al. and also an acoustic scattering model developed by Ansley Layton over these volatiles distributions to help predict what the actual gas flow rate is. So when we do that, we get that we have a range of gas flow rates from about 90.7 meters cubed per day to about 1,200 meters cubed per day. And those represent the 5th and the 95th percentiles of the data that we see from the short-term record. When we compare that to estimates that we observed in previous studies, it's about on the same order of magnitude of our 95th percentile. So this provides some kind of way to obtain estimates just using acoustic data set itself. But one of the perks about this is also with that classification that can possibly be used in different fields, such as fisheries when we're looking at discrete targets within the water column. And so with that, I would like to just acknowledge the different funding sources that helped throughout all of this process. And I do want to emphasize just the importance that the center had in the training throughout the process. A lot of this work was done with the help of Tom Weber, who was my advisor, and a lot of the skill sets that I was able to acquire from him and a lot of the other researchers here at CCOM. So that's an important note that I want to take with me.
I'll talk about the work of the Multibeam Advisory Committee, which I said was in part, well, mostly NSF sponsored, but there's tremendous overlap with our interests. And of course, we support some of these efforts too. Get through. Yeah.
So my name is Paul Johnson, and I am going to be talking about a couple different three topics here. The Multibeam Advisory Committee, some Multibeam evaluation tools, and some app services that we host here at the center. Come on, let's move. There we go. So the Multibeam Advisory Committee, also known as the MAC, is actually composed of three people. It's myself, it's Vicky Farini, who's a senior research scientist and associate director at Lamont, and Kevin Jerem, who is on remotely right now. We have been funded since 2011 by the National Science Foundation to support the U.S. academic research fleet. And our primary goal is to ensure the consistent high collection of high quality data by the fleet. And we've been doing this by providing onboard and remote support for the ships and the technicians on the ships, standardizing the protocols and tools that are used for system acceptance testing, documenting, reporting, and publishing system performance results. So everything we do is available to the community at large, and also sharing best practices and lessons learned. So the U.S. academic fleet is actually 12 vessels. It's 11 research vessels. And we also support the U.S. Coast Guard icebreaker Healy. Amongst those 12 vessels, there's 16 Kongsberg systems. So, and they kind of run the gamut from EM 710, 712s, which are kind of 70 to 100 kilohertz systems, EM 302, which is kind of the midwater, the 30 kilohertz system, and then the 12 kilohertz EM 122 and 124 systems. These are the deep water systems. There's also 2 Rezon shallow water systems in the fleet. Currently, there aren't any EM 2040s, unlike the NOAA fleet, but that will be changing as there's 3 RCRVs coming online starting next year. And these will have EM 304s and 2040s. So, as I said, one of the big things that we tried to do is kind of standardize the approach to system performance testing. And we did this by basically setting a set protocol that we do testing for all ships, whether they be new or used, and also we report on every one of them in a consistent way. So there's kind of 3 test modes that we work in, and there's a lot of overlap between these different test modes. But the first one is the system acceptance test, also known as an SAT, and this is where we establish the baseline performance of a new installation. So it's critical to know how system works when it's like brand new. So you can then monitor later on to see if there's been any degradation of the system. We've done 9 SATs, including 2 in the last year, which were conducted on the Sally Ride in Atlantis. And we also do what are called QATs, or quality assurance tests. And this is to monitor the performance of existing systems. So we will tend to do these when ships are exiting shipyards or on demand by the ship. So some ships actually have us out about once a year or so, just to make sure everything's all right. We've done 4 of these in the last year, including on the Kuliak, Atlantis, Killamoana, and the Healy. And the final is acoustic noise testing. We've done 7 of these, and you can do some testing through kind of, using built-in self-tests and stuff on the Kongsberg systems. But if we have a serious acoustic noise issue, we also have people that we can bring in that can really kind of ring out the systems for us. So our kind of face to the world is our website, and it's available at mac.unals.org. So this is out there for anyone to go to. And this is where we host our technical reports. So for every visit we do, whether it be in person or virtual, we have a report that's generated. So we also host non-academic research reports. So if you look, you'll find 11 OCS and OE reports there from Okeanis, from a whole bunch of ships. So I mean, this isn't just for the U.S. academic research fleet. There's also numerous other reports from other institutes that operate vessels that are outside the fleet, such as OET and Falcor and a bunch of others. There's also a link to our help desk through the website, and this is basically where we receive questions from technicians and operators and scientists of the academic fleet. And the reason I kind of highlighted the scientist part is because they are often some of those critical eyes on the data. Like one of the problems that we have with the academic research fleet is that the multibeam is just one system that the techs have to support. There's nobody generally on the ship that's overlooking it. So when a scientist can get out there and they say, hey, we think we see a problem, they'll contact us, and that will usually kick into motion, a visit from us, or at least a discussion with the techs about what's going on. Our website also has links to some technical resources and presentations that we've done in the past. New this year is an ocean mapping community wiki. And this has been kind of spearheaded by Shannon Hoy at OE, Colleen Peters, Saildrone, Kevin Jerem, and the MAC kind of hosting the whole thing. And the purpose and vision of this is it's a public resource to improve data quality for everyone. It's easily updated, it's easily searchable, and it's easy to share this information. It's a platform discussion and troubleshooting, and we've tried to make it as welcoming and accessible and respectful for everyone. That said, it is not a standard operating procedure place. You should see ocean best practices if you want to go down that road. It's also not a replacement for any of the manufacturer's guidance on how things should be done. We do provide links back to the manufacturer's documentation, but we're not hosting it ourselves. And the site is really not meant to be either promotional, preferential, or judgmental. So one of the topics that you can find on the Ocean Mapping Wiki is a whole section on dimensional control. And this is a topic that we run into all the time when dealing with ships. Like there's a lack of information about sensors, like where is the phase center for this antenna? What does your system want? So we've tried to put in links to like all of that kind of information. Another very common topic seems to be waterline, with the confusion about what is waterline. Waterline is not necessarily draft, and these things kind of get intermixed all the time. So we've been trying to spell this kind of common misconceptions and common problems, so that it's not just us that know this. Anybody can go in, they can do a search on these kind of things and find out at least what we know or the contributors know. There's information about how to conduct a survey, or what to ask your marine surveyor to collect in order to have a quality survey. And there's also a whole section on axes and sign conventions. This is kind of how you would interact with it. Basically, you can go in, you can do a search on a topic. So you want to know about EM 2040 power issues, or you wanted to know anything. All the different discussions are tagged, so not like they're trying to make it more easily accessible for people to find things. There's also a whole section that basically tells you, how do you contribute? How do you make your first post? And there's also a wish list, which kind of highlights kind of some of the areas that we need help filling out, or if there's topics that you're interested in, it can be added here. So I'm going to say this is new as of this year. So this is kind of something that's still being filled out, and we gladly welcome contribution to it. There's also a section on assessment tools and the data collection behind those tools. So this, sorry, my formatting is messed up on the screen, but in this section, basically, I mentioned that we have developed tools and stuff that we use for assessments. So this here kind of explains the theory behind it. How do you collect the data for it? How do you go in and actually do the work with the tools and that kind of stuff? And you can actually also links to where you could download the tools from. And we have kind of 4 main tools that are available right now. And these are the tools that we use. There's a file trimmer tool, which is predominantly for the older Kongsberg systems that were collecting .all files, but it allows you to kind of compress the raw file sizes by removing unnecessary datagrams. There's a built-in self-test plotter. This is for doing plotting of RX noise data, or you can also do TX channels and RX channel impedance measurements. So that would be these kind of plots up in here. This is a noise plot. There is swath coverage plotter, and this is basically plotting your swath width as a function of depth. And in this case, you can see it's overlaying a historic data set. So this could be used, one, to kind of determine, what kind of swath widths am I going to get from my survey when you're laying out a survey plan. But it can also be used for monitoring for issues that you might have with the system. So if you see a significant decrease in your swath width as a function of depth, you probably know you have a problem with your multibeam or with the shit with noise. The tool can also plot up the depth mode that is being collected in. It can plot up the ping mode, and it can plot up backscatter strength and things like that. The tool, we also have a tool that's a swath accuracy plotter, and this will allow you to basically take a reference surface, which is a high density collected surface, run cross lines over it, and then plot up how well the cross lines compare to your reference surface. I was just going to say one of the updates. So these tools are in continual development. One of the most recent updates is the ability to basically scan through a whole collection of raw files. So you can take your KMLs or your .all files, and say somebody at some point actually changed with the waterline value by mistake. You can actually scan an entire year's worth of data and say, when did this change happen? It'll pop up, and you can kind of go through and then fix the records after that. Larry mentioned this earlier. One of the other things that we're currently working on, and this is kind of a project that we're picking back up that had been under development before, is basically making multi-beam system assessment site database. So this is going to be kind of a collection of all of the sites that we use, sites that for the MAC, sites that we use outside, and any contributed sites. And we hope to have basically anything where you do a patch test, accuracy testing, swap performance testing, backscatter testing, water column testing, whatever. And with that, we'll have linkages out to the line plans, and we'll have linkages to the acquisition settings that were used for that area. And if there's a cruise report generated, we'll link to that. So right now, this is kind of on my desktop GIS, but the plan is to actually make this all available through a web interface. And speaking of web interfaces, that's where I'll go now. So the center has actually been running some form of kind of web services for maps and data since about 2012. Kind of gone through a variety of different generations of this software, starting with just a GIS server and making it a GIS server portal. And we're currently using a GIS server portal and a data store. And through this whole time, we've been offering a pretty wide variety of services and web applications, including collaborative data assessment web app. So this is a tool that we've used with the JEPCO grid for the last 3 years. And during the review process, we have reviewers scattered around the world that need to be able to look at the data and kind of assess the quality of the data. So you also don't want people looking at the data until it's actually ready. So everything's secure behind a password. People are able to log in. They can easily draw polygons with a tool around an area. A web form pops up, it collects that information. It's all ingested into a central database, and then which can then be exported and given to whoever needs to do the review of the data. So this has been a really successful tool that we've used, like I said, for the last 3 years. We also host a Gulf of Maine web app. So this actually dates back to our earliest services in 2012, which started with just our summer hydro services. In the last few years, Larry Ward, Michael Boganko, and myself finalized kind of an expanded region, which now includes Western Gulf of Maine, Long Island, and Southern New England. And it's available at this kind of horrible address, but basically here you can find the backscatter maps, you can find navigation, you can find like a regional view and a high resolution. And we're also kind of testing things like the ability to download areas and that kind of stuff with this. We also have services for all of our extended continental shelf surveys. And here you can kind of go in, you can interact with the data. We have some story maps talking about the collection of the data. We have 3D viewers like for the Marianas. The bathymetry is available through there. The backscatter is available through there. The navigation's there. You can click on the navigation, find out what files were done, collected that area. So we developed a lot of this kind of stuff when we were actually building the products. And this kind of fell out that, well, these are kind of handy services to have available for everyone. And finally, the last app I was going to highlight was kind of doing some large data set visualizations. In this case, using the JEPCO 2022 data set. So we have layers that have been built. It's a bathymetry layer, elevation layer, a type identifier layer, and also an indirect measurement mask. So when you see the black layer come on right there, that's basically hiding all of the areas that are not the result of a direct measurement. This is a tiled data set. We gave it a 5 times vertical exaggeration to kind of make it pop up a little more. And this is available for anyone to use. And there's also another version of it that you can go in, you can do profiles of the bathymetry and kind of pull out more information. So coming soon is everything I'm showing here has been on our server called maps.ccom.unh.edu. We actually, as of last week, set up a brand new server, which is online, mostly online, but it should be available to everyone. And this is actually, we're going to migrate all of the center's web services to our existing server is actually going to transition that into a development server, but it's also going to be used for doing some OECI service testing and kind of exploring what can be done with that. And that's it.
All right. Well, good afternoon, everyone. So my name is Jenn Dijkstra, and I'm a research associate professor here at the Center for Coast Dimension Mapping in the Joint Hydrographic Center. I'm going to present today task 29, which is the management, and this is a new task within the grant. And so this is management of marine living resources from ECS and ISAT-2 data. And this is a very collaborative project where we're working with Oregon State University as well as the Mote Marine Laboratory. And the goal of the project is really to investigate the use of multiple platforms that have different sensors and resolutions for repeat mapping approaches to characterize and detect changes in coral reef ecosystems. The project directly supports Goal 4.2, and I'm a little sad Nicole's not here. The NOAA Blue Economy Strategic Plan, where its objective is to assess, restore, and protect American coral reef systems. And this can be achieved concurrently with IOCM and hydro survey objectives.
Andy, do you know what Nicole's schedule is in terms of the call? I'm wondering, we might swap presentations, so, because I think this is very relevant to
Okay.
Nicole.
Yes, okay, great.
Jen, just wait a minute.
Sorry.
Goes till 3.
To 3, okay.
Just go. I'm good, yeah. Yeah, okay. All right, so the data can be collected for and used for multiple purposes, and this is going to be a theme throughout this presentation. So for example, for multibeam data, it can meet IHO S-44 standards for safety of navigation, hydrographic surveys, and can be submitted to NOAA's external source data team for evaluation for application to nautical charts. It can also be used for IOCM purposes in terms of hydrographic survey planning, prioritization, marine resource monitoring and mapping, and management. And then survey areas that are navigationally and economically important, but maybe skirting that null line. All right, so the outline of the talk, given that this is a new task within the grant, I'll provide a general overview of the project, the data sets that have been collected, and the kind of multiple ways in which we're utilizing these data sets. And so our study sites are located in the lower Florida Keys, and they're identified by these yellow pins here. These yellow boxes represent marine sanctuary sites. And so right now we have 6 sites, and these sites were prioritized, one, because 2 of them are national marine sanctuary sites, Sand Key and Eastern Dry Rocks, and one, which is Eastern Dry Rocks, is a mission iconic reef site. These sites were also prioritized or considered as high priority areas for mapping by NOAA's Restoration Center, the Florida Keys National Marine Sanctuary, as well as the National Coral Reef Monitoring Program. So here, these are just zoomed in maps of our sites. And so it's a little busy, but hopefully not too busy, where here again, these yellow boxes are the sanctuary sites. The black lines represent areas where ISAT-2 data is available. And the starred areas are our study sites. And as you can see, and this is Sand Key, which again is a marine sanctuary, and Eastern Dry Rocks, which is a marine sanctuary as well. And Eastern Dry Rocks is also, just to remind you, part of the Mission Iconic Reefs program. And so the data that's being collected at these sites are unmanned aerial survey data, stereo imagery, which is collected by divers. So we have high resolution data, multi-beam data, as well as single beam. And we were fortunate enough to go to these sites in 2021. We went to 3 sites, Site C, Acer, and Haslunds. And don't worry about the names. And then again, we were fortunate enough to go back in June of 2022, where we resurveyed these 3 sites and then added these 3 additional ones. And the data that we are collecting and processing is also being used by NCOS to aid with their Mission Iconic Reef Imagery Visualization Project, as well as they're using our locations as test sites for co-registering their forthcoming AUV imaging efforts, and they actually might be down there right now doing that. And so these data sets are also going to be used to create workflows as well as customized algorithms for optimal integration to essentially create a bathymetry map with associated uncertainties. And so this will be the PhD thesis of Selena Lambert from Oregon State University, and Chris is her advisor. And as you can imagine, assembling these data sets that have various quite different spatial resolutions, they'll have different accuracies, as well as different coverage extents, is going to be pretty challenging, but we're confident that it can be done. And we're hoping that the techniques that we develop can then be extended to data sets beyond the Florida Keys, beyond this project. We're also interested in comparing surface metrics from these various data sets. And so, for example, one of the surface metrics that is often used is rugosity, which is here in this yellow line. And what we're interested in is comparing rugosity values spatially, so across our different sites, and also temporally within our different sites, or within a site where we have multiple years of data collection. And then also across various platforms. We're also leveraging the imagery to build spatial analysis tools, and specifically designed, at least for now, for underwater structure from motion data sets. And so this is spearheaded by Kindred, who's somewhere here, I believe, hopefully, and Tom. And Kindred is a PhD student here at the center. And so what they're doing is they're using our models, and this is an example of a model that we create. And then they're calculating rugosity values. So essentially creating a rugosity heat map where you have periods low, where the cool colors represent low rugosity values and then warm colors represent high rugosity values. And we're really doing this because oftentimes you create a scene, you import that scene into something like Flatermass or ArcGIS, and you get a simple value, and that value is based on a defined spatial scale. But oftentimes we are not necessarily interested in a single value of an entire seascape. We're really interested maybe in this rugosity value right here where the corals are outplanted. And corals are often outplanted in clusters. And so because of that, we want to know not what's going on for this whole reef, but what's going on right here. And oftentimes too, with fish are really drawn to areas with high rugosity. And so if you know an area, and so if you know along the reef you have an area of high rugosity, that could be an area that you want to identify as maybe one that you want to look for fish. And so here, this is an example of this, where essentially rugosity changes as a function of the spatial resolution at which it is calculated. And this is user defined. So the user is defining the spatial resolution at which rugosity is calculated. And so here, it might be a better. And so this is a video, yes. So this is a video actually that shows you how the user is manipulating spatial resolution to calculate rugosity and how that changes kind of the rugosity within your scene. The maximum rugosity value, which is over here. And what's really great is that it's dynamic. It works on this 3D scene. It's user defined. And it works on pretty much any three-dimensional scene. sorry. There we go. All right. So we're also leveraging these images to understand a little bit more about how we can use these images or 3D models for monitoring coral reefs. And so my graduate student, Glenna, here she is, she's measuring the coral in situ, so diver collected measurements. We've created this nice orthomosaic, and this is just a subset or a subset of that orthomosaic, and you can see she's measuring the polygons here. And so we are essentially comparing our in situ measurements with those of orthomosaics. And that's again to determine how well do they correlate, what is the accuracy. And we're also doing this using terrain, our 3D models, where again, here's the coral, Glenna's measured it underwater, and then she's also measured it in our 3D model. And again, this is to see how accurate is that 3D model compared to our in situ measurements, and can you use orthomosaics and the 3D models to look for change in coral reefs at this finer resolution. And finally, we are essentially leveraging all the ground truth data and the LiDAR data that's in the Florida Keys to explore ISAT-2 data for detection of marine resources. And this is spearheaded by Yuri Raznov and Kim Boll and Gabby Trudeau. She is an incoming PhD student who will start in the fall and really kind of delve into a little bit more with the ISAT-2 data. But here, so some of the questions we're asking is, how does data quality vary with season? And here are some examples of that. And sometimes it's the data is great and sometimes not so good. And so, and then we're also looking at multi-temporality with it as well. And so with ISAT-2 data, it goes to the same location every 91 days or so. And so the question is, can you use that to either for monitoring purposes or for kind of repeat mapping of a location? And so I just want to say that this is like, we all kind of love working together, working on this project. There's multiple PIs and PhD students involved in it, and from multiple institutions as well. So, thank you.
All right, thank you for the introduction. As you said, my name is Mike, and I'm here today to talk with you guys about some of the work we've been doing on propagation modeling of multibeam echo sounders. So we always want to kind of keep the context of why we're doing this. And so in both the old grant as well as the new grant, we've had this programmatic priority to investigate both the transmit radiation characteristics of the multibeam, as well as particularly the potential for these systems to contribute to the local soundscape, as well as the potential to impact marine life. And a lot of that effort has, as we mentioned before, focused on the SCORE series of experiments where we took a multi-beam echo sounder out to a Navy hydrophone range. We collected a bunch of acoustic and oceanographic, as well as marine mammal tracking data at this Navy site. And we learned a lot from this experiment. We improved our capability to model these systems. We were able to get some of the first direct measurements of the deep water multibeam, as well as we were able to track and observe the behavior of a local resident beak whale population that is at that range. And all this work, in particular, the marine mammal work, has really helped us understand the potential impact case for multibeam echo sounders. But we need to remember that all this work was done with one system at one particular place with one set of marine mammals. And we as users use a variety of systems and a variety of multibeams and we can't always take them, ring up the Navy to measure the systems. So we want to actually be able to assess the biological impact by using models, and we want to have confidence that these models are accurate and relevant. So that brings me to a really interesting opportunity that we had back in June to attend a modeling workshop. This workshop was sponsored by the EMP Sound and Marine Life Joint Industry Program, which has primarily been a lot of representatives from the oil and gas industry. And they bring together this interdisciplinary group for this meeting to kind of look at the acoustic sources that are used in that industry and try to come to an understanding of what the models are giving us, as well as what are potentially relevant biological impact metrics. And so, as I said, it's an interdisciplinary group. So we have engineers from the field, we have acoustic modelers, bioacousticians, as well as even representatives from the regulatory end of things. And so everyone gets together and tries to have this holistic discussion about what's going on with these acoustic sources that we're using. And again, this is oil and gas, but also very relevant to us as we try to use these systems as well. So historically, this has gone on for some years, and they are primarily focused on using modeling these air gun arrays, or air guns and air gun arrays that they do their seismic work with. However, this year they expanded their focus a bit, and they began to look at ship noise as well as the multi-beam echo sounders. And so what we did in this workshop is we actually gave the participants 8 different scenarios prior to arriving out in the UK, and we tasked them with modeling. Well, they tasked us with modeling these scenarios. And the scenarios are split into 2 different themes, so to speak. We have verification, where each modeler brings their results, and they compare them, and they argue, and they say, are we getting the same answers? Are we getting close? And try to come to some kind of common agreement with respect to the models. And then the second set of scenarios involve taking the models, which are now in tentative agreement, and comparing them to actual data within the actual collective empirical data, seeing if what we model matches reality. So in that regards, I'm happy to say that the center was able to be an active and heavy participant in this workshop. Initially, we were approached to provide the SCORE data set as one of those validation scenarios. But as we continued to work with them, we became more and more involved to the point where we helped author the multi-beam scenario, and we were able to go and participate in this event as modelers. And participation wasn't limited just to myself. A former student of ours who was there as a BOEM representative, Christos, was also there to help present some of the work we've done on the SCORE range. So, and the summation of that is to essentially say that we were the resident experts on multibeam for this event. Shifting gears a little bit, we now want to kind of look at what we did from a modeling perspective. And I don't want to get into a lot of the math and physics. What I want to do is just kind of share the scenarios, see how they build upon each other, and give you some key takeaways. So here we have this kind of typical setup where we have a source. This is a building block scenario, a very simple source, a monopole, essentially radiating sound in all directions, placed within the water column. We were tasked with calculating propagation loss. We sometimes call it transmission loss as well. Within this environment, which has been fully defined with sound speed profiles and sediment speed profiles. And so I did the modeling for this, and the type of model that I used is called bellhop. It's a very time-tested, well-known model that uses ray-based theory. And when I say ray-based theory, what I mean is that the model uses rays to track the acoustic energy as it moves through the environment, refracting, reflecting off the sea surface or the sediments, sediment basement. And it takes all those rays and their interactions and translates that to a propagation loss type function. So here you can see the results in range going out to 30 kilometers versus 1,500 meters in depth for the bellhop model, this monopole source. And the main thing that we're going to take away from this is that this is a refraction kind of limited environment. There's only so much energy that can reach certain areas within the environment. So this is a building block scenario. The whole point of it is to get everyone to agree on the environment and the physics before we introduce anything really complicated like an air gun or multi-beam. And actually stimulated quite a bit of discussion, in particular because everyone who models air guns are in this kind of low frequency range of 10 to 1,000 hertz. And so when they have sound that enters the sediment, it often comes out of the sediment and affects the results that we measure in the water. But for our systems, the multi-beams, this purple line, you can see it's flat, meaning that we can pretty much safely ignore our contribution in the sediment. And so that's kind of the environmental setup that propagated through the rest of the models. We can now turn our attention to the actual modeling of the multi-beam. So for this scenario, we chose a typical deep water multi-beam. Here are the individual elements that comprise it. It's got a center frequency of 12 kilohertz, source level 240 dB, and it features most of the kind of advanced technologies that we see in the systems we use in the field. So we have individual sectors as well as array weighting, all the way down to the individual element directivity patterns that get coupled into this work. And so again, tasked with modeling it. This is the resultant transmit radiation patterns for our multi-beam. And I don't want to really dig into it. What I do want to take home from this was that, again, this is a very diverse group of people. And the concept of what a sector was not well understood. And so when we were able to show that the multi-beam has 7 independent steered transmit sectors that don't overlap in time, this was a bit of an eye-opening thing for everybody. The other thing I want to draw your attention to that came out of the source modeling was this discussion on source level. So when I say that our system has a 240 dB source level, this is reference to 1 micropascal at 1 meter away. And for a lot of people, if you sat 1 meter away, they would think that you might actually experience 240 dB of sound, but that's not actually the case. Because these systems are so large relative to the sound wavelengths that they put out, what ends up happening is they have this region of space very close to the array. It's called the near field that reduces the effective source level that's generated by the array. And so this is an important thing to consider when we try and do these models, particularly when we're trying to look at something like an area of impact underneath the array. So it's kind of a running theme that got carried forward through the propagation modeling. So now we can actually look at the propagation modeling. We did this for a couple of different acoustical metrics that we commonly use and look at when we do biological assessment studies. And in this case, we're starting with sound pressure level. We think about sound pressure level or SPL in terms of either RMS, so over a small time window, or SPL peak, which is the maximal instantaneous pressure that you would experience in the field. And we calculated this for various ranges and depths. And you can see, this is SPL in color, range, depth. We did this for a couple bearings, or in other words, we measured out to 10 kilometers that way, and that way for the 90-degree bearing. For in a long track, we would calculate SPL in the fore aft. We also looked at this kind of side lobe regime, which was a bearing of 45 degrees. Now, in order to do this modeling, I chose to do 2 models, and I chose these models specifically because it would give us a really good way to look at the impact and what happens in the near field. See, the bellhop model, which I described before, can be augmented with a radiation pattern that we calculated on the prior slide. And yeah, so we can use that, and that'll properly model the field and the refraction and the multi-beam or the multipath, but it won't necessarily get the near field right. Versus the isovelocity time series, which uses a time series approach, and it's far more computationally expensive, but it's capable of getting the near field right. So if we look at some of the selected results, what you're looking at here is range versus SPL, or depth of 20 meters, depth of 1,000 meters, and we're looking at bearing 90 versus 45. And the main point I want to share with you is that when we look at that bellhop model, they may not necessarily get the near field right. It's actually overestimating the level. So bellhop, like I said, it's a common model to use, whereas the isovelocity model, I don't think I've ever really seen anyone use it. It's really computationally difficult, but it shows just how much we may be overestimating the sound pressure levels near the array. And in the same case for the bearing 45, we actually see the same effect. Again, these are on the order of about 10 dB, 10 to 15. And this effect is observed all the way out to ranges of about a kilometer away. So that's quite a bit of overestimation demonstrated between those two models, and why we need to really kind of look at the near field effect. I did mention RMS versus peak. This box plot just compares the RMS level versus the peak level. And what it essentially boils down to is that there's a 6 to 7 dB difference between these metrics. So if you're using a model that can't calculate peak sound pressure level, which something like bellhop cannot, you can kind of give yourself a upper bounds to what the peak pressure level would be. The other type of model, or the other type of metric that we like to look at is sound exposure level. Sound exposure level is kind of like the cumulative exposure, energy exposure along a period of time. And so in our case of modeling, we actually had a 3,000 second long transect where the ship drove along the x-axis and it pinged once every 10 seconds. The vessel moved 40 meters per second. So within that time period, you have about 300 pings. And we would measure the SEL for various depths and ranges along the y-axis. And for this, I chose two different models. And what I wanted to explore in this case was how important it was, how important the main beam exposure is versus the entire cumulative track. So this multipath coupled sonar equation is a mouthful, but it essentially equates to accounting for all 300 pings that occur within that track, as well as the multipath. So you'll have about 900 exposure events going into your SEL calculation for this scenario. Whereas the bellhop main beam exposure, we're again using bellhop since it's so robust and useful, converting its output to sound exposure level. And then we modify that by saying how many times does a source located within the environment actually get exposed to just the main beam. And so that's a much less rigorous treatment of the actual SEL calculation. And we compare those two. So when you look at the models, we have bellhop in blue, sonar equation 1 in orange. You should ignore from 1 kilohertz out because the orange one is not well suited to the refraction effects. But where they're supposed to be compared in 0 to 1 or all the way for the depth of 1,000 meters, you can see that they are like right on top of each other. And so the point to take from that is that what's really driving your metric here is how many times you're exposed to the main beam in this transect. The other thing, I like to keep the context of why we're doing this present, and this wasn't part of the workshop necessarily, but I took the South Hall threshold levels for impact, and I superimposed them on the SEL calculation. And this shows you kind of an aerial impact. It's hard to see in white, sorry about that, where we're exceeding those thresholds. So in this case, for our multi-beam that we've modeled, we're looking at about a potential impact out to 50 meters either side. And so that's most of what I wanted to discuss. The takeaways here, we were an active participant in this workshop, and we provided a lot of expertise. We really were able to stress to this interdisciplinary group the importance of accurately approaching modeling the multi-beam. Taking shortcuts is not really possible for this type of system. And we also looked at 4 different models, which were used to compute relevant acoustic metrics. And between the two models, we kind of have 2 takeaway points. One, on SPL analysis, we really need to take care of the near field. And for the SEL models, we note that if you're going to model this, the main beam exposures are some of the more important things to consider. What's next? Well, I think the workshop report is going to be publicly available. It's currently still in development. And we also have the hope to do a special issue in 2023, which we'll actively write an article for. And that's all I got.
Okay, and Christos got off the plane even more recently than me, so.
Yeah, so I'll stay with my notes just in case. I mean, I'm only with 2 hours of sleep. So hello, everyone. Thanks, Larry, for the introduction. Thank you, everyone, for being here. So I'm Christos, as Larry said, and this slide
Just speak up.
This slide summarizes the projects I have been involved in the past 12 months with demonstrated progress. But due to the limited time, today I'm going to talk about the depth uncertainty visualization. Depth uncertainty visualization, our efforts towards an automated chart compilation process. And I'm going to say a few words about our participation to the CHC 2022 Speed Mapping Challenge. So maritime accident reports have showed that bathymetric data quality is one of the chart-related causes of maritime accidents, which could have been prevented if the data quality had been better accounted for. Until we fully map the seabed with new technologies, mariners will have to navigate with charts compiled of data of varying quality. So as this table here shows data from 32 nations, almost 50 or maybe more than 50% of coastal ENCs are compiled with data of poor quality, whereas only a small portion is compiled with data of A1 or A2 quality data. Of course, beyond coastal waters, the situation is even worse. To mitigate the risks, mariners tend to follow previously used routes as good practice. However, for example, before that, this is an example of the routes extracted from our routes of the SIP project towards the route suggestion and the route prediction system from historic AIS data. For good practice, as I said, mariners tend to follow these routes, but however, there are instances, situations that they need to take a route for the first time or deviate stray from a planned route for reasons such as extreme weather or ship handling to avoid collision in confined waters. And this is when the ships are in the greatest risk of grounding. The normal process for the prudent mariner is to begin with plotting an approximate route, assess it for the presence of dangers, and modify it accordingly. In performing the task, it is essential that the data quality information, as is encoded in our known CAPZOC, the category of zone of confidence, is taken into account by the mariner. So previous studies confirm that indeed mariners take CAPZOC into account, which is also confirmed by the data we collected for a survey I'm going to present in a while. And this provides automated safety checks within a user-defined search distance from the plotted route. However, the problem with this method is that dangers may remain undetected if a small buffer is selected, or others not being real threats for the plotted route due to the distance from the route could be highlighted by such a large value, a large buffer for the ZORC is selected. This is something that contributes to the mariners' fatigue, the user fatigue, and increases the chance for actual dangers to be disregarded or inadequately assessed. In the specific example with a small buffer, the two shallows here, oops. You want to do your magic, Mike? Okay. Yeah. So as I was saying, with a small buffer, come on. Yep. So with a small buffer, these two shallows may be missed. These two I was trying to show, whereas with a large buffer value, okay. Yeah, it's good. Okay, I'll try to keep up with. So as part of our work on the integration and visualization of bathymetric data uncertainty, we have investigated other methods of integration. However, today I'm going to focus on the visualization aspect of things and the development of a new coding scheme in place of the problematic star symbology. Now, what are the problems of the star symbology? First and foremost, the considerable clutter that's on the screen. Text are often impossible to read. Those, for example, the pointing arrows. And contrary to cartographic practice, star symbology adds more visual weight to the areas of high quality data instead of the low quality data. It is not intuitive, and this could be me. I'm still counting after 25 years in the field. They may not fit in small areas like the question marks you see here, and continuous zoom in and out is required because of the clutter and the problem I said about the depths and all that stuff. And of course, they dominate the screen, particularly in dusk and ECDIS modes. And so the actual question is, can we do better than that? We believe we can. Therefore, we determine a set of requirements that the new symbology must meet, satisfy, so to become effective in the new for the application, such as minimal interfere with charted information and be easy to remember. It is important to point out here that the study focused on the new ENC S101 ENC quality of bathymetric data and the new naming convention 1 through 5. Subsequently, we evaluated the suitability of the visual variables for the application, and for various reasons, each of the visual variables seemed ineffective, problematic in satisfying one or more of the set requirements. The solution that seemed most promising is the use of see-through textures created by combining visual variables. The advantage of using textures is that they are minimally used in current active displays, and if they consist of open meshes, they are expected to minimally interfere with other chart information, while they can be intuitive and they can achieve a good visual hierarchy. These are the two proposed coding schemes, countable textures of lines and dot clusters. The main principle is that the number of lines or the dots correspond to the quality of bathymetric data. So one line or one dot for quality 1, 2 crossing lines or double dots for quality 2, 3 crossing lines, 1 single, 1 double for quality 3, and so on. For comparison, we developed 2 color-based schemes based on ideas previously expressed within the hydrographic community, one using opaque colors and one with different levels of color lightness and transparency. To overcome the problems of color fields, such as obscuring the underlying bathymetry and color blending, we developed the color textures coding scheme. This is how the 5 schemes look over a section of a chart. And before we discuss the survey and the results, using the textures of lines, I would like to demonstrate how the proposed solution can improve things, especially compared to the star symbology. Beginning with the clutter problem. This is a ZOC A1, quality 1 area with stars and lines. The stars, as we said, obscure the overlapping depth labels, whereas with the lines, the labels are now clearly visible. The top figure here is the visualization of quality 1, and this is the same area with a quality 4 assigned, with stars and lines. With stars, the worst quality 4 is less crowded, as you can see, compared to quality 1. However, again, the symbols clutter the overlapping depths. On the contrary, lines add more visual weight to the worst quality data to act as a warning for the end user, for the mariner. However, as you can see, labels remain still readable. We already saw the problem with stars, clearly not intuitive, whereas with the countable textures, this shouldn't be any problem anymore with the one-to-one correspondence, and she looks happier, I think. Concerning the problem with star symbols that may not fit in small areas or become ambiguous in small areas, things are also improved. And lastly, the problem with stars dominating the screen. This is stars and lines in day bright, and in dusk mode, bathymetry now stands out, as you can see, and becomes the top layer. To test the performance of the 5 coding schemes, we ran an online survey for professional mariners and other working with charts. Disseminated to end users with the support of 3 maritime centers. We have established collaborations. The survey consisted of 4 sections: the consent, introduction, evaluation, and demographic section. And in evaluation section, in area 1, all 6 quality categories are visualized. Same in area 1 dusk, which was meant to test the coding schemes in the dusk mode. Whereas in area 2, 2 data quality areas are displayed, and in area 3, only 1. participants were asked to rate the performance of the coding schemes using a 0 through 6 Likert scale, where 0 was for exceptionally bad performance and 6 for exceptionally good performance of the coding scheme. There was also one objective multiple choice question where we asked participants to answer what is the ZOC category in the area 3. After the 4 evaluation areas, we asked participants to rank the 5 coding schemes from worst to best in both day and dusk ECDIS modes. To supplement the Mariner survey, we also carried out an objective laboratory experiment using synthetic chart displays, a project we reported in 2021. The task of the participants was to enter the quality of bathymetric data where the marker appeared, and 2 experiments were carried out, one with and one without the legend display. Response times and errors were the dependent variables of the experiment. Summarize the results. The 2 proposed countable textures of lines and dot clusters performed the best and second best in user rankings in both day and dusk ECDIS modes. Together, they received more than 70 and 60% of user best rankings. Lines received the most positive ratings overall. Besides being participants' first choice in rankings, Lines was also had also the highest mean rating throughout the survey. And it was the only coding scheme with mean ratings over 3 in all 4 evaluation areas and against the 5 requirements. It was followed by opaque colors and dot clusters. Dot clusters failed in area 2 and area 1 just, and requirements 3 and 5. 3 is the quality of the coding scheme to emphasize worse quality data, and requirement 5 to be effective in all ECDIS modes. Opaque colors failed in area 3 and requirement 4, which is the easy to remember requirement. However, although not shown here, the detailed analysis of the individual questions revealed so that it actually failed the ECDIS mode as well. Transparent color and color textures performed generally worse than the other 3, and particularly the color textures that failed in most survey questions, as you can see. In the survey objective question, which was what is the ZOC in this area, dot clusters and lines resulted in the least error rates and best evaluation in the subsequent subjective questions, which again, due to the limited time, are not shown here. Likewise, in the objective experiment, the dot clusters produced the fastest response times and lowest error rates, followed by lines and opaque colors. The transparent colors generally performed worse in both situations. Lastly, the analysis showed that textures, as I said, were the most preferred coding schemes, lines being the best overall, as I said. However, the 3 color-based schemes received a large portion of participants' best rankings as well. This and the hierarchical clustering analysis that revealed a cluster of the lines and dot clusters in user ratings and rankings, and one broad cluster of the 3 color-based schemes suggests that 2 groups of users exist, one with preference to textures and one with preference to colors. So to accommodate preferences, more than one visualization techniques could be made available in the new generation ENCs. Before closing, ratings showed that those who were aware of the star symbology and its problems rated significantly higher the coding scheme, so they were clearly happier with all 5 coding schemes. Okay, so time for a quick stop for hydration, sorry. Before we switch from data visualization to a data generalization project. In 2018, the Office of Cost Survey announced the rescheming of the chart portfolio where more than 7,000 cells would replace the 1,000+ suite of charts. In these past 4 years, NCD has completed the production of approximately 13% of the cells, something that demonstrates the great effort that NCD cartographers have put into the project, but on the other hand, also demonstrates the immense amount of effort and time that is required for the compilation of the remaining cells and the completion of the project. The main challenge of the project is the compilation of bathymetry due to the transition from the imperial to the metric system, and especially since the respective tasks remain largely manual. For instance, this illustrates the approach of depth areas compilation with color coding soundings and tracing the boundaries. And this is the sounding generalization, where soundings are selected among this insanely dense data set. Automation of these two tasks and others could alleviate some of the burden for MCT cartographers and of course expedite the process. Automation of map production is the holy grail of cartography. And as efforts in the land domain have demonstrated, this is indeed possible to a great extent. However, particularly due to the safety constraint we have in our domain, algorithms, workflows, and solutions developed for topo mapping are not directly applicable to nautical charting. Our vision is a fully automated solution, and the production of nautical charts from a high level of detail of authoritative source database. However, in the short term, the expectation from this project is to model the nautical chart compilation process while investigating methods to modify and implement existing algorithms and workflows. In the context of Tamer Nada's PhD, from the available national and international cartographic standards, we extracted the therein-to constraints, rules, and guidelines, and compiled a template that defines the conditions to be respected, a hierarchy level, and the pseudocode of each condition. This is an abstract, high-level representation of the model developed in the S3 environment, where a number of sub-models, the themes, are responsible for the generalization of the source data set. Each theme contains various tools responsible for solving a generalization problem, and the generalization spreadsheet is the one that controls the generalization operator and the criteria to trigger or stop the generalization. The model builds upon the concept of macro, meso, and micro agents, where macro are the highest in priority and also control the meso and micro. It's the same for the other two. Now, instead of a detailed review of the workflow, which I don't think will be useful today, let's have a look at some examples. This is our first test bed. I recently compiled band 5, 1 to 20K cell in the Puget Sound that served for the development of the model, testing the consistency of the process and the evaluation of the outputs. These are two model outputs in their relative sizes after the scale change, but to make things a bit easier, I'm switching to same size figures. Of course, you can't say much unless you closely investigate the data here. So due to the limited time, let's move on. In order to support the risk-scheme efforts, one needs to combine multiple cells to derive a smaller scale cell. The model can do that, and it merges the depths, the aerial features and the linear features such as depth areas and depth contours for the generalization and the final output. This is an example of 16 band 5 cells going to one band 4 cell. The model can even work when edge matching issues exist, such as these two. In the output, the two endpoints are connected with straight line segments, which can be manually edited by the cartographer, but the depth areas and the lines are one single feature now. The model also works, meaning it doesn't crash in this particular case, where bigger inconsistencies exist among the neighboring cells, such as different sequence of depth curves intervals. But of course, it cannot merge the depth areas to produce one single depth area. Now, another real world general case scenario we investigated was combining different band cells for going to the target scale. This is an example of combining 7 band 5 cells and 1 band 4 cell to go to one generalized band 4 cell. The model utilizes generalization tools that are available with ArcPro. These are generic tools that don't have the safety constraints we have in nautical charting. So we expected that errors, safety violations would exist in the first place. So however, that said, to have a model that it's useful and that someone can use, we needed at least to highlight these safety violations for user fixing. So here is the output of a custom tool that highlights the depth area safety violations. And although a correct product in the first place is desirable, an iterative process where a user or a new tool fixes the errors and these are brought back into the model for further processing seems realistic for the time being. So to summarize, what we don't have and we don't expect to have, at least in the near future, is a plug-and-play software that produces charts on demand from the source database with one or a few clicks. We are not there yet. What we have been working on is building the model that we can leverage to achieve the goal of automation. And the model in its current phase is flexible and allows us to adopt existing or future algorithms, tools that work sufficiently for the application towards the final end goal of automation. And moving to our third topic for today, the work I just presented was essential in winning the speed mapping challenge initiated by the Canadian Hydrographic Service, the Canadian Hydrographic Association, and the COMREN. The scope of the competition was to prototype a cartographic production chain using open data and free software. The work by our team named SEGU United, where SEGU stands for the nationalities of the team members, was ranked first unanimously by all judges. I'm going to say a few words about our efforts to meet the evaluation criteria of the speed mapping challenge, which could explain what we did well and possibly what we did better than the other teams. There are two big categories, the methodology and cartographic representation criteria. For the use of open data and free software, we built upon our previous experience with work such as that by Jose Cordero on free and open source software for ocean mapping, and that of Stelios Kondaris on web map services. So to enrich the Canada vector data that were made available to participants, we accessed sources such as NCI, Sentinel Hub, OpenStreetMap, and Google Earth to do things such as acquire bathymetry in unsurveyed areas, and also find conspicuous and other important chart features such as churches, chimneys, piers, lights, and other, and also to separate natural from man-made shorelines. We used various open source software for querying and accessing data, and as well for processing and visualizing data. Safe deep bias contours were ensured by incorporating a semi-automatic approach where often automatically generating the contours using the double buffering method. This red line, we manually traced always on the deep side to fix errors and give them a more natural shape. For the soundings, we built upon a cartographic sounding selection with null dyer, which derives the surface critical points that corresponds to least depth, shallows, deeps, and supporting soundings. And also, we used our sounding validation project to ensure the salt bias nature of the selection and also to enhance it where necessary. For the topology, we built upon Tamer Nada's work that I discussed previously and developed custom tools to verify that there were no gaps or overlaps between the skin of the earth features or things such as self-crossing of lines. The legibility of soundings was ensured by our label-based hydrographic selection with null dyer. And we did other things beyond the requirements, such as reprocessing elevation contours to provide a more accurate, realistic description of the terrain. Now, for the flexibility and robustness of the work, that was demonstrated by the selection of two very different sites, different areas, and the automation of as much as possible of the entire process. So our work on the speed mapping challenge illustrated the efforts that we have been working in several projects. We have developed national and international collaborations. So we are building this environment of having at some point charts on demand and speed up the cartographic process. And also the work I discussed about the speed mapping challenge is something that we can easily modify for other users and providing data to other customers as well, such as MSDI or another user-friendly NC-like base map for JETCO or whatever. And that concludes my presentation. Thank you for your attention.
My name is Val Schmidt, and I lead the autonomous systems group here in the lab. And there's a cadre of us, KG and Andy and Roland and Avery. Don't tell them I said that. I'm going to talk about a whole bunch of research and engineering projects that we've been working on, and I'm going to talk about a bunch of operations that we've done with Drix 8, and then I'll talk a little bit about Drix 12. Yeah, so we have a mobile command unit. We call it the mobile, the van, the mobile control van. It's that white box up there. And we've taken it on a couple of great expeditions, both to Thunder Bay National Marine Sanctuary. We park this thing on the shore and we send a ASV out to survey for weeks at a go and operate it from shore. And we've got it kitted out with VHF radios, an AIS receiver, and a PTZ camera, and all kinds of large format displays. It's really a great way to operate. I think for the NRTs maybe, but we really enjoyed a lot, and we've made some upgrades to it this season that I thought I would talk about. Of course, the range that we can get to the ASV, which in this, like our setup is on the order of 10 and sometimes as long as, well, routinely 10, always 10, often as much as 15, and on a good day out to 20 kilometers away is largely dependent on the height of our antenna, but this is kind of dangerous to set up. So we've got a fancy new system to get it upright. But then the other thing that we've done is put directional antennas on it for the non-MBR radio systems, the higher bandwidth ones. So you have a directional antenna, you're only pointing in one direction. If your ASV is over there, that's a problem. So we put an antenna rotator on it and we ROS enabled it. So ROS stands for Robotic Operating System. And that's kind of an open source middleware for pushing data around within robots. It's the same middleware that XBlue uses and the Dijkstra that Kongsberg uses and the Hughes and a whole bunch of other folks use the same middleware. So we ROS enabled it. So now when Ben, our ASV, which is the yellow boat in the white lab over there, is running around, the antenna just tracks it because we know where Ben is and we track it automatically. That's kind of fun. We also stole Larry's Starlink and put it on top of our control van. So now we have internet service no matter where we go. And we've been doing some tests with this just in the past few days. We had an intern like push the button a whole bunch of times to do speed tests and get a sense of the throughput. So download speed like 125 megabit per second and upload speed sort of 4 to maybe 5 megabits per second. And then I wrote a script to collect a whole bunch of data, 1,000 plus measurements every minute over a couple of days. Actually, I just pulled this data yesterday. And so here you can see if you think you need sort of 2 megabits per second to run your ASV and collect all of the data back continuously, you can be insured to get that sort of 80% of the time, and 20% of the time you may not get that. So this is not a big data set by any chance, like we'll make more measurements, but it's nice to get a sense of what we can expect from this new technology that's like global coverage, and there's marine units coming. And the other thing that's nice to know is although there are some measurements for which there's not a lot of throughput, there's not, at least in this tiny data set, which is like 5 hours long or something, there's no sustained dropouts in it like you sometimes see in Iridium and that kind of stuff. So this is encouraging, I think, and we'll keep looking at this some more. So I talked about ROS. On top of ROS as a middleware, we've written our own software for driving robotic boats, and we call it Project 11. It's our like marine robotics framework. And we've made a bunch of sort of incremental upgrades to this. One of them is the ability to consider temporal navigation objectives. So what does that mean? So you can have like a path and speeds that you want to go to get to each point along that path. And that's one way to do it. But if you want to miss targets, what you really want is a path and times associated so that I want to get to this point at this time and this point at that time and this point at that time. And that allows you to predict where other vessels are going to go and ensure that you don't hit them along the way. So it's like kind of the same thing, but a different like mental model for the robot. And it's the way roboticists think about these things. And so we added that to our ability. We have a technology, a piece of software we call UDP Bridge, and it transmits data between endpoints over radio links between different ROS environments. And it compresses data on the fly, and it handles things like dropouts in your telemetry system and all that kind of stuff really robustly in a way that ROS does not. And we've added a bunch of features to that to make sure that when we have big packets over that we don't tend to lose them as much as we did. And then we wrote a new utility called Bag Manager, but this is going to be totally confusing because the robotic operating system, they have their own log files and they're called bag files. So this is not a hydrographic bag. This is like a data file that has all manner of like a binary file that has all manner of data from the robot. So a bunch of it is time series data, could be everything from engine RPM to electrical compartment temperature and whatever. But you can have images in there and LiDAR data and whatever else. It's just the log file format for RAWs. And we view those logs in this utility called Foxglove Studio. It's an open source package that's really nice because you can have synchronized views of all these different data streams, and you can have 3D views of LiDAR point clouds or radar point clouds and images and maps all embedded in one thing with one big time slider across the bottom. The only problem is that only allows you to view data from a single file at once. So what Bag Manager allows us to do is take a whole bunch of log files that have been rotated through over the course of a long deployment and slice them and dice them and pick out the topics that we want to look at to inspect. And we've open sourced this, put this out to the rest of the robotics community for other people to use it as well. CAMP stands for CCOM Autonomous Mission Planner. And this is our GUI and map display for interacting with our robotic boats, for doing mission planning, all that kind of stuff. So this interacts directly with Project 11, which runs on the boat. And we've made some upgrades to this. And for the first time, we can now handle multiple platforms in CAMP at once. So you can select one ASV, plan its missions, push a button, off it goes. Pick another ASV, plan its mission, off it goes. Those could be service vehicles. In the OECI work that we've done, we've interfaced it with underwater vehicles, the buoy vehicles. And then I wrote crewed and uncrewed systems. But crewed systems, like, are you going to mission plan for a crewed system? What does that mean? Well, not only does this GUI like allow you to do mission planning, but it also, and I don't have it's like not displayed here very well, but radar overlays come in on top of this from the vehicle, all the AIS targets that come back. So you could have a manned vehicle, for example, that's over here, that's got an AIS receiver that detects some big ship coming, and your ASV over there, and maybe the ASV doesn't detect that AIS transmission, but all of that data would show up here for an operator. So an operator has a much bigger and wider view. So we're excited about that because it provides lots of flexibility and functionality to collect data from different sources and provide it not just what's coming from the ASV, but from other boats as well. So I talked about UDP Bridge. We've added some neat functionality to this and a GUI to control it. And what it allows us to do is not just send data between two endpoints, but send data between kind of any endpoint between these different RAWs environments. So you could connect to a boat and choose which topics you want to advertise out of that boat. And you could be someplace else and choose which topics you want to subscribe to. And to give you an example of how neat this is and powerful, when Nautilus was out deploying DRIX off the coast of Hawaii this past year, we were having a difficult time docking, the automated docking method with the LiDAR. And we were able to sit here and log into to the Nautilus and to the DRIX, and then request the LiDAR point cloud data over that entire link, over the satellite, all the way back to engineers here to view in Foxglove in real time. And you're like, okay, why would you do that? Why would you look at it in real time and not just like log the file locally and look at it afterwards? But if you think about the expense of getting out there, while you're docking, you have the entire deck is manned, the captain is on the bridge, and you're trying to make it work, and for whatever reason, it's not working. And the expense of trying it a couple of times, logging some data, and then sending that data to France or someplace else to try to figure out what was going on, and then going and doing it again, versus like having somebody on the phone who's looking at the data that you are looking at and says, oh, you need to dial this knob, that'll fix your problem. It's big, it's great. So we're excited about this functionality, and we think that's really
I
neat.
can attest to that. Being on the ship end, it is big.
Okay, we have another project that we call Matilda because I can't think of an acronym with all those silly letters, but the idea is we take the full suite of sensors that we would have on a robotic boat. So a camera, radar, and AIS receiver, GPS and IMU, all that kind of stuff, and package it up in a portable package that we can put on any other vessel or mount on the end of our pier or whatever. And the idea is to use those data sets to kind of self-annotate each other in a way that we can then use that self-annotated data in machine learning algorithms going forward. So like as an example, there's already algorithms, we didn't invent these algorithms, but that can recognize a boat and a camera image. But if we take that boat that's been identified, if it also has AIS data, then we immediately know how far away that boat was, how fast it's going, what kind of boat it was, what its relative speed and direction is relative to us. So we might be able to then retrain this algorithm to tell us all of that stuff, like make a guess from the image alone without the AIS data for all the ships that aren't transmitting AIS. So you see some ship out there, if I'm the mariner, I can say, okay, that's a sailboat. I would guess he's doing about 5 knots. That's probably about 4 kilometers away, maybe. And he has pointed that way and not that way. And we'd like to have like an algorithm that can do that on the boat as well. Okay. We have had a bunch of students over the years work on path planning algorithms for robotic boats for safe navigation. And we realized that we needed to build an architecture so that they could put their different path planning algorithms into our boat, and we could make like a apples to apples comparison between them so that we were to figure out which ones are doing well and which ones are not. And in the process of that, we realized, there's probably not one path planning algorithm to rule them all. Like you might want one for transiting and a different one for survey and a different one for approaching the dock, and you want to switch between those on the fly. So this past year, we put in place a plug-in architecture for these path planning algorithms so that we can swap between them and do that without a lot of pain. And as we have new students coming in, we can have like a very clean sort of interface that they can code up against. John already talked about Lynette Davis's work. When she first came, she was working on this water column mapping stuff actually for robot boats. And in the end, she did it for operators. But it's great actually, because we can suck the data out like in a step before she makes a plot for a human operator and make a same kind of plot for a robotic boat. And so in follow-on work, we're going to start working on algorithms to auto-detect those transitions that Don was talking about and make those available to a AI-based navigator. In 2018, we had a student graduate with a master's degree, and he was working out how to teach a robot boat to interpret and navigate on an electronic nautical chart. And this was a great piece of work. We spent a lot of time thinking about compilation scale and how you make that like knowledge, like how you translate that and all the quirks of charts, how you translate that for a robot boat. We've now formalized all of this in a new tool that is open source. And now we take the entire archive of ENCs and the position of where the boat is and automatically take the appropriate scale, the highest scale of chart for where you are, and turn it into a risk map that's based on many of the things that Sam worked on in his thesis. And this is called an occupancy grid, but that's just a fancy word of the way robot boats often navigate and determine risk along the way. We've also done the same kind of thing, occupancy grid with the radar data, and then follow-on work, we'll start working on some collision avoidance kinds of things for our boats. Okay, so now I'm going to sort of switch gears a little bit and talk about some of the things that fell out from DRICS 8 operations and the OECI funded stuff, because these are the things that either were follow-on work that we worked on after the fact, after the OECI work was done, because it had big impact on the pending acquisition of DRICS 12, or in particular for hydrographic operations and the cruise that was happening with DRICS 8 that was survey related that Andy and Larry just got back from. So, I should back up maybe. So there have been, Larry mentioned there's 3 cruises that have happened this past year with DRICS 8. One was an integration cruise aboard the Nautilus in March. And then there was that tech challenge cruise with all the Woods Hole underwater vehicles in May. And then the OCS mapping sponsored cruise, they just ended a week ago. So after the integration go on the Nautilus, we wrote a big report and we presented this to the folks at the UAS Operations Center, Bill and Company, in great detail, both orally and in written form, about all the things that worked and didn't work, and what was hard and what we fixed and what was still outstanding. And so we tried to provide as much information as we could. We also sat down with Russ Metzler and James Corville. Russ actually came here to the lab and we spent a whole morning talking about shipboard recommendations for USV operations, about how to set up a command center on a ship and what all of that might look like and what has worked for us and what hasn't. And that was all towards Class B requirements, kind of things that they're working on. In the run up to the Tech Challenge cruise, Don Jones came out and he was terrific, like jumped right in and helped us with all of the mobilization for that. So installing everything on the ship for the very first time, there was a new crane and a painter boom, and the first time that we had assembling the Drix out of containers. So there was a lot to do. He also knows all the greatest dim sum places in Hawaii, so he'd love to come with us anytime. But it was great to have him out there. And again, this was all in preparation for the arrival of Drix 12. And then this last 2022 expedition that Larry's going to pronounce the name of for us. But this was all in preparation to make sure that these guys were in good shape and ready to go. Part of the work that fell out of the Drix 8 operations, it started while I was in quarantine getting ready to get on the ship, but then we've refined it since, is building an endurance model for the Drix, not just like a fixed thing, but like a mathematical model that we can change the parameters of. So we've got plots like distance and nautical miles versus speed. If you start from 100% fuel at a bunch of different power levels, like hotel loads. So if you got all your sonars on it, it's a higher power level. If you don't have them on, it's something less. So you might ask the question, how far can you go at 8 knots at a full tank of gas? And if you look at the plot over there, it's somewhere on the order of 700 nautical miles. Or you might ask, can I ride out a 3-day storm at 7 knots? So this plot is time to empty in days versus speed. And so yes, at 7 knots, you got to be able to ride out a 3-day storm. This one is fuel level and percent versus time. So if my survey, I think, is going to take 50 hours, can I do this at 8 knots? Well, no, you probably can't, but you can probably do it at 7 knots. These are tools that we're providing for the operators so that they can make decisions of not only about their survey plans, but then if something goes wrong and they've got to make the weather comes up and you didn't expect it, or plans change for the ship or whatever, for whatever reason, you can't bring it back on board right away, you can make real-time operational decisions about this stuff. So as an example, weather conditions and seas were not great where they were surveying at Nihoa, which is 120 nautical miles away roughly from Kauai. So they came here and deployed the Drix here in the lee of the island. And then we came up with a plan, we here came up with a plan for them so that what time should they deploy here? How long is the transit going to take? What speed should they go so that they have plenty of fuel to survey during daylight hours, because the permit required that, and then survey back with plenty of, or transit back with plenty of extra fuel at the end of that. And their actual plan was a little bit different than this because the weather changed and they were able to stay on site longer and then recover while they were out there. But it's a great example of how understanding that system and how all that nuance is really important. When Drix 8 was delivered, so Drix 8 has EK80 systems also in the gondola in addition to the EM2040. And Drix 8 kind of has a self-noise problem at 200 kilohertz at the sort of main frequency that it has in there. And so it's in the electrical system provided by the Drix, and with help from Alex de Robertis and others, we built a power line filter for that and installed it in Drix 8 in a hurry, actually, because we were afraid that Drix 12 might have the same problem, and we wanted to make sure, see if this would fix it for Drix 8 so there wasn't such an experiment when Drix 12 came. It does, in fact, lower the self noise levels for Drix 8, but probably not enough. We probably have more to do there. And it turns out for Drix 12, because you guys paid for a new gondola and we just the old design of the gondola, your new gondola has all the electronics for the EK80 in the gondola, and you don't actually have this problem. But we were ready if you did. The Drix joystick-based remote controller that you can drive around the boat with, it operates nominally at 915 megahertz or something like that. And for whatever reason, it blasts RF outside the band like a lot, and it interferes with the L2 frequency and GPS and with marine star corrections. And this took us a long time to figure out because Drix 8 docks into a docking system that's covered on the top, so you don't get GPS except when you're out. And when you're out, you often turn off this RC controller, well, turn off the transmitter from this RC controller and plug it in, and it then operates over your your radio connection for like IP stuff, so the NBR or Wi-Fi or whatever. So it was like nefarious to figure out what was going on and why we would sometimes have problems with this. And we finally figured it out, and we bought a filter which totally fixes the problem, and Drix 12 has one of those filters in it. So you're all good. There were lots of challenges in our OECI operations for multi-vehicle ops that became apparent to us and are going to become painfully apparent to you once you start deploying multiple vehicles. So for us, we had vehicles with different weather windows. So that was like really challenging to figure out which vehicles you could deploy when, and the dance of retrieval and this weather model was used a lot to find short periods where you could hide behind the lee of an island to deploy or recover one vehicle or another. Another is casualty planning. Like you got to figure out if you have two vehicles that have problems, which one you're going to neglect while you're like handling the other one. And that's like a real thing. And then the mean time between failures of a system of systems. So, you know, the mean time between failures of a whole bunch of different things is always going to be shorter than the shortest one. And if they're all the same, if they're all like, you have a failure every 2 weeks and you have two things, now, if each individual one has a failure every 2 weeks and you have two things, then the system has a failure every 1 week on average. And it just goes, so the point is the systems have got to be reliable. Like you got to spend a lot of effort to try to make them as reliable as you can get them. Deck crew fatigue. We have vehicles coming on and off the boats all the time. And when we had multiple vehicles in the water, we just wore everybody out. And that's a real thing as well. And this is going to sound dumb. There's a lot of really smart people on all of the ships that I've worked on. And I tend to think I know something about networking. And on every deployment, we have had a real struggle, either integrating the ASV into the ship's network or getting the various vehicles to talk to each other. And I'm not even talking about the political aspects of that or the policy aspects. I'm talking about the technical aspects are equally challenging. And that's something that we're going to learn some more about. Okay, so Drix 12 arrived just a couple of weeks ago, August 2nd, in a big box. And this was before like NOAA folks arrived and Xblue arrived. So we, it was like Christmas, so we packed everything and took an inventory, like photographic inventory of the entire shoot match. And then with the help of the Xblue folks and the NOAA folks as they arrived, we assembled everything and put it all together. This is all the transducers going into the gondola at the bottom and all the bits and pieces. So this facility is at the Olson Center for Advanced Manufacturing, which is a couple of miles off campus. But it's a terrific facility with big overhead cranes, and it's a bit of a dance getting everything out of the containers and assembled, but it's really nice. And then on the trailer and down to the pier, the sea acceptance test for Drix 12 was like a week long and well, maybe 10 days, including the weekend. We didn't go out on the weekend, but I think it went really well. There's a few things that are outstanding as you might imagine, like, and those are things, you know, some of them are like material problems and some of them are like, boy, I wish the vehicle did this, and which I think is healthy. In fact, Alex Durabertis, he said, I went into this thinking of like, there were a few things I was really worried about. And he's like, and those, most of which I'm not worried about anymore. And there's a few things that I was not worried about that I'm like really worried about now. And I think that's kind of a healthy attitude about the whole thing. But Yeah. Mike Gallagher, like if you guys know him, like, that was fun. And, like his, you can just imagine people driving it around. Okay, so this is gonna be just a brief video of what the interface looks like when you're doing over the horizon operations. And although DRIX 8 has a little bit of that capability, as it doesn't have an Iridium Certus system, which provides a higher bandwidth over the horizon capability, which DRIX 12 has. So this was new for us as well. And I'll just explain what you're going to see. So this is it's called the HMI, but the map display for the DRIX with the radar overlay. This is an infrared camera that is providing a video feed in real time. That's a still camera, a still image of from one of the peripheral video cameras that are looking around the side. So when you're operating via satellite, you can click on, maybe I don't know how this works. Yeah, you can click on one of these little triangles there. One of those triangles there and get a still image from each of the other directions. And then the monitor above, you're going to see an image of the SIS data acquisition display from the 2040, and it's a screenshot. So there's not enough bandwidth to do like a remote desktop connection into the Windows computer that's on the boat for Certus. But what XBlue has provided is an interface that you can configure the sonar and a way to query for screenshots of the display so that you can get some feedback of what's going on. So let me play this real quick. So it's a little maybe more jumpy being played through our computer here than it is in real life. This is actually very smooth in real life, and this updates very smoothly as well. But yeah, that's a really unfortunate video of a representation of what real life looks like. I don't know what's going on, but yeah, you get the idea. Actually, we were all really sort of surprised that this worked as well as it did. We were kind of impressed with that. This was my backup slide. If that didn't work, which it kind of didn't, but whatever. Oh, I should point out, I forgot to mention, so this is the DRIX passing data through an Iridium Certus system up to satellite, then to the public internet, then to the Starlink system, satellites again. So it's probably going back down to the Earth, then back up to another satellite, right? And then back down to the antenna on top of our control van, which is sitting on the UNH pier. And the DRIX was like 6 miles offshore. So like that's a pretty circuitous route, but actually works pretty well.
Val, is it valid to mention that Iridium link may well become redundant, and that will be a Starlink link also in the not too distant future?
Yeah, I mean, if you sort of like that sort of nominal bandwidth, so I've never made a plot like I did for Starlink for this Iridium system, which would be kind of interesting to people who are expensive.
I guarantee it's much less.
The Starlink is definitely much less, but
No, the Starlink link is much faster than the Iridium Certus link.
Yeah, that's my point. But what I don't know is like, that kind of distribution of connection throughputs is kind of interesting to know, like how frequently it's bad and how frequently it's really good. But it's like your point, it's like an order of magnitude different in throughput between those two systems, and at least one order of magnitude less expensive. I think probably more than that actually. So so fingers crossed that Starlink hangs out, stays around. This was data from the 2040 on the DRIX 12. Like, we haven't scrutinized this like as a good hydrographer should, other to say that like it's self-consistent and it actually doesn't look too bad at first blush. But like folks at the TJ will get out their magnifying glass and sort all that out. Okay, so this was a picture from 2019, but that's where the DRIX is going next. To Cleveland to meet the Thomas Jefferson to get integrated onto the TJ and actually go out and do hydrographic work. And actually, the training that was meant to happen here this summer is actually going to happen. XBlue folks will be out there and we'll be training 4 or 5 folks in the operational part of DRIX while it's out there. Yeah, I had the same picture as Larry did. I know. And that's all I have. And I don't know if I have any time, but I'm certainly happy to answer questions.
All right, good afternoon, everybody. As Larry said, Ryan Calder. I'm going to talk about bathymetry now, and two different types of bathymetry. Bathymetry that's volunteered to start with, and then bathymetry in the sense that we normally talk about in terms of high definition surveys. Let's start with volunteer bathymetry data. I don't like the term crowdsource. I prefer volunteers. Typically, there isn't a crowd, but if you've heard it talk about crowdsourced bathymetry, it's the same sort of idea. This project started because I was asked by CBA 2030 to make recommendations for loggers that we could use to collect data for various places around the world. And I made those recommendations, but to be perfectly frank, I wasn't very convinced about any of the data loggers that were available. For what they do, they're very expensive. They're about $250 each. I cracked open a couple of them and had a look inside. There's not really that much inside them. And this led me to the question that's here, which is, what is the minimal costs, minimal functionality system that I could build that would allow us to collect data from volunteers in the field and make sure that data is actually useful for some purpose, whether that's CBA 2030 or to go with hydrographic data or something in between. The key is system here. If I just generate a data logger, it's relatively straightforward to do. We're not actually doing a lot of technology here, but that's only really part of the story. A lot of the systems generate just the hardware piece, but then what do I do with the data once I've got it? What format is it in? What processing needs to get done and so on. So what we're proposing here, what we built with the aid of a couple of likely characters that you see here, there, is an entire system where we provide everything you need to collect and then use your own volunteer data. And the reason for doing it this way, and in addition as an open source project, is we don't want to be data collectors. If there's a central data collector, that limits how fast you can scale out your problem. What we want to do is to make an entire system so that anybody who wants to collect their own data can just clone this system and collect their own data. So the local yacht club wants to collect their own data, they have everything they need to do it. Now, they may not necessarily want to build their own hardware, but at least they'll be able to buy the hardware if that's what they wanted to do. So in our scheme here, just to walk you through it, the idea is we have a hardware data logger, which we provide all the design files to build them yourself. When the ship comes back into the dock, a local technician would go out and use the mobile app that we provide to suck the data off the logger by Wi-Fi. That then gets sent up into the cloud. In this particular instance, we're using Amazon Web Services. As soon as you upload it, that triggers the processing to start. We dump some intermediate data so you can do other things with it. And then that triggers a second process to start, which then sends data to DCTV in the appropriate format with the right metadata and so on. Because these are very carefully designed to minimize the cost, you can build them for relatively cheap. We call this the project the wireless inexpensive for a reason. The bathymetry logger or Wibble. Prices vary depending on where the current chip shortage is for now. But last time we priced them out, they were about $10 roughly each. If you build them in batches of 50, you add connectors in a box, maybe you double that. But that's still an order of magnitude cheaper than the alternatives which are there. And because these things are only turned on when you need them, they're guaranteed to only use as much compute power as you have data coming in. So you keep these relatively low cost. This is cents to do processing of typical files. So we designed that all last year. Since then, we've been kicking the tires, taking it out into the field, making sure it's actually working. The first expedition we did with it was to the Northwest Passage with the Healy. And I installed it on the Healy with the most convoluted data collection system you'd believe, because they couldn't give us a straight EMA feed. We had to work around it. We got that working. I collected data all the way through. You can see there was a couple of small surveys that we did when we had a little extra time there, and ended up here in Greenland. This project allowed us to make sure that everything was working. It taught us a lot about what sort of facilities the logger actually had to have. And it also lets us then prototype the entire end-to-end system. If you notice, this is actually an NCEI website. And so we worked with them to make sure that the data was getting put into the right format, so it showed up in the databases exactly the way that they wanted it to minimize the effort they need to put it in. This is actually a prototype of their new point store. They were kind enough to read this data into us to demonstrate that process. We also took it out into the field with an actual civilian. This was a journalist who asked us, she was writing a book about mapping the oceans, and when I told her we had this log, oh, that's great, can I have one? Okay, so we put it in a box, sent it out, and with the aid of her husband, she was able to, not that she couldn't have done it herself, but she had no electronics background, so her husband has. She was able to install it on their, I think it's a Boston whaler, like a central console small boat, and go out and collect some data in San Diego Harbor. So this is something that's designed to be able to be installed by the end user, and I think we can demonstrate that that is in fact the case there. We've subsequently made a bunch of these. We have a few more to get made. We're working with our colleagues at Comment at USF. We already sent them one version like this. We've got another 4 to send them. We're working right now with our friends at CIDCO in Canada. They came up to me after I did a talk about this at the Canadian Hydrographic conference and said, this is right along the lines of what we're doing. We should work together on this. So we're very hopeful that we're going to send them a couple of boards to test with, and we hope that we become development partners as well to help us move this project along. Like I said, it's an open source project. If you do get involved, if you want to do it, I'm happy to give you the details later on. We've also been able to use it as a test bed to prototype new methods for dealing with this type of data. It's always better if you can give a concrete example for how something should work if you're trying to convince a committee to do the right thing. This particular example, we had to develop new metadata for the next generation of the IHO working group on this, just approved by IRCC. It'll be going into a circular letter in the next couple of weeks, I think. What we did was we used WBBL as a test bed to demonstrate how we can put all of the metadata actually into the logger, which then preserves it into the files, which preserves it over the mobile segment and into the cloud, so that we can assemble it all in the cloud, all in one piece. And not only were we able to work out how to do a more rational sort of metadata, we demonstrated how it could work in practice as well. And that went a long way to convincing people that it was a good method to actually use. There's also been a lot of work going on behind the scenes here. Ryan Miles, who's sat up in the back corner there, programmer extraordinaire, and all-round solid chap, has been working on the things that I'm not very good at, like adding tests and doing continuous integration and how you package up for distribution and so on. So it's a much more robust code base than it was previously. We also worked with a computer science team of 4, and the outer 2, both Jason, just to make things confusing, are still working on the project with us, actually volunteering to work on the project. They enjoyed this much. They not only did they rewrite the mobile data collection to make it cross-platform, they also reworked this workflow for the cloud as well, so that instead of having this strictly linear flow, which is the minimum requirement, which to guarantee the data gets to NGDC, I'm showing you how old I am, NCEI. They've also redesigned it so this thing can actually be dynamically retooled even depending on the data that's coming in. So you have a much more flexible flow, so that if in your particular implementation you need to do something like, for example, tee off the data so it goes to your local hydrographic organization, because that's sometimes required depending on where you are in the world, you can do it in a much more efficient manner than we were doing it previously. So there's lots going on behind the scenes there. I want to move on now to talking about how we do something useful with this data. This is a quote that I love. Is Pete Wills, who's the CHS Pacific, he's also vice chair of the IHO working group. And he had actually worked with a whole bunch of data from BCDB, and this was his lament, just working out, how can I trust this data? How much can I trust this data? Which of this data do I trust more than the others? And I couldn't agree more with this sentiment. And so what we've done in the past is work out a methodology for assessing the reputation, the reliability of individual observers. It's based, I won't go into the details of it, it's based on how you do chess rankings effectively. And what we do is we evaluate in blue there the reputation up to about 3,000, arbitrary scale, of how good we think the observer is, which changes dynamically. So that if you're doing well for a bit and then your performance starts to drop off, your reputation goes down. This is based on an idea of comparison against authoritative data from a database like MBES, for example, or ECDB or other charting databases. But what we've been doing this time around is to think about how we might use that in the context of the data itself. So I would argue that you could say that there should be a transitive relationship between your observer and your data. So the data at the point of observation inherits the reputation of the observer. So if your observer is authoritative, your data should also be marked as authoritative to start with. And then over time, it may start to decay. Or it may not, we don't know for sure, but at least it should be independent then of its observer. And why that's important is if we think about the survey priority and data and archival data and the duration, how long should we keep data in the archive before we declare that data is no longer actually useful for us? Where should we go to do our surveys next with the limited resources we have? Well, ideally where the data is least good, right? Or where there are big ships and shallow water, whatever the requirements are. We want to have a rational way, a principled way of deciding when the data is good, when the data is not good. And so we can apply the same ideas of reputation to the data itself. So data reputation on the vertical axis now against time. At the point of survey, the data is considered to be authoritative because the observer is. Over time, we don't observe it again. So we can't say that the reputation has gone down, but we can say that its uncertainty has gone up as a function of time. And then the question is, what happens when we then make another observation? And what I'd argue again is that one of two things can happen. Either the observations that we make agree with the data that's in the database currently, in which case it should reinforce its reputation. The uncertainty starts to drop down again, and we change the reputation. Or it disagrees. And if it disagrees, then we should start to reduce what we believe to be the data's reputation away from being authoritative, because more recent observations tell us that's not what's there now. And the rate at which this drops is a function of how good the observer is. So if your volunteer is a really good observer who normally gets things right, then you should drop the reputation of the data in the archive more quickly than you would if it's some random guy with a passport. By way of example, ignore these two. These are the uncertainties. It's a really interesting story, but not one we have time for today. There are two observers here. This one we would consider to be essentially authoritative, the best of breed of a volunteer observer. This one less so. You can see that the data reputation here is being adjusted as a function of time as more observations run along, and that could be from one observer or many, doesn't matter. And as we show that there is a significant difference in depth, in this case 5 meters, between the new observations and what's in the archive, you can see the data reputation in the archive dropping off as a function of time. As a hydrographic office, if you choose a particular threshold and you say, data with reputation lower than this threshold has no place in my database, then this tells you how long you have to wait, how many observations you need to see, depending on the reputation of the observer, before you declare that data is no good. Remove it from the database, age it out, we'll do another survey, trigger an NRT to go have a look, whatever it happens to be, but in a principled manner, rather than just going, that looks about good to me, which is, we do a little bit better than that right now, but that's traditionally what we've done. Where you set that threshold is up to you. That's a risk factor for the hydrographic organization. But at least in this sense, if you have better observers or poorer observers, it automatically adapts to the reputation of the observer. So it gives you the sort of dynamics that I think we want to have in this problem. There's more to do here, obviously, but I think it's headed in the right direction at least. There's a lot of technology behind the scenes here. Again, Brian Miles has been doing the things I'm not good at, adding tests and continuous integration and rewriting this in Python so we can go into the cloud more easily. Patrick, whose spiffed up version is sitting over here, has been doing this also as his thesis work, where what he's doing is working out how to make this actually automated. So for example, when we look for source data, we want to go to DCDV to go grab that source data. When we're looking for authoritative data for reference, we want to go to MBES and grab that. We're using Utopo at the minute, but ideally we want to go into the room database. And has a tool that's been building, it allows us to go out and find the right things, wrangle them together, package them up, and make them available for doing the data analysis, which has been a big step forward into making this into a practical reality. Ideally, what I'd like to do is to see this all deployed as part of the processing that I was talking about in the voluntary data previously. We're not quite there yet, but we're heading in that direction. So I want to start talking about bathymetry in the sense that we normally talk about it, high resolution surveys, conventional hydrographic surveys. Do a couple of updates first. Previously, we've talked about how we estimate data density and therefore resolution when we do surveys with the chart algorithm. The algorithm we built originally was based on the idea of Multibeam data. It doesn't work so well if you have LiDAR. We rebuilt that algorithm with a thing we call level of aggregation for LiDAR. We never quite got it back into the mainstream chart algorithm that everybody shares for all the implementations that are done. Our friends at Leidos, for a variety of reasons, really needed that to happen, so they've been helping us to get that done. We now have a pull request to get that into the main chart source code. That will happen hopefully after this week is done. We also thought last year about releasing the source code for the Cube algorithm. It's been nearly 20 years now since that Cube algorithm was originally licensed, 2003. And we talked to all of our industrial partners. None of them complained. Well, industrial partners that have licenses, none of them complained. So this is now open source and our MIT license, and you can get it from our repository. Among other things, let people actually see how it works. It also means it can get included into open source projects like Cluster, for example. And so Cluster, because Eric is in NOAA and was able to see the algorithms early, the implementation without a cluster almost as soon as the database, the repository became public. We've also been working with looking at enhancing algorithms like chart with machine learning techniques, especially for LiDAR. Kim Lowe, who's back over there, has been working on the theory for how we do this, and Brian's been working on doing the software engineering behind the scenes on that one. The change here this year is that instead of thinking about trying to classify the points and seeing if we match NOAA's classifications, what we're doing instead is looking at, do we generate the same depths? Are we functionally equivalent rather than identical in classification? The good news is that essentially hands-off, we don't quite agree entirely on exactly how hands-off, but mostly hands-off. In about 80% of all of the tiles that we've looked at in LiDAR, and including some very difficult tiles, the correlation in depth is extremely good, and the differences are tiny. So we think we have something which is really getting towards being a very robust way of doing processing for this. And the work that Brian's been doing in the background to get this ready for implementation, I think we're heading towards something that we could transition into, at least into demonstration mode, so that we could have people kick the tires and see how well it works. Now, finally, I want to start talking about the cloud. And this is work that's sponsored in part by our friends, the OACI. So thank you. I can't really see you because the lights are staying over there. Thank you. Everybody's very excited about the idea of working in the cloud. We are too. But we have to be careful, I think, about how we do it, because if we do it wrong, we might end up with significantly suboptimal results, because getting the data into the cloud is usually free. But what happens once it's in the cloud is not free. Getting data out generally is not free. And so if we're going to do this right, first thing we observe is that if your data goes into the cloud, your processing must follow, and vice versa. You don't really have an option. It's kind of all or nothing, really, if you're going to be efficient. And then we have to work out how we do this well, so we don't end up paying exorbitant costs. One of the suggestions for how this might be done is, let's take our desktop software that we use right now, stick it into the cloud, and we go, okay, we're done. That's our cloud strategy. There's been a couple of anecdotal examples of that. We did one here. Paul set up a server here with Nautilus. But we didn't really have any strong evidence about what happened. To be honest, that idea twitched my bogometer off scale right. I really was not convinced about it, but I had no evidence. So what we suggested was, let's just try. And so we selected 3 different hardware configurations, 1 local at the top there and 2 in the cloud, and a variety of different storage options, 2 local and 3 in the cloud. And by the time we do all the combinations of things, we end up with about 58 different configurations there, which we then say, well, let's run them a little bit to get some statistics. We do 10 iterations of each. It takes a while to do it and slog through it all, but at least it will give us a solid basis for making the decision. I could go into a lot of detail of the result. Let me just show you the data set that we used. It's a Okeanos Explorer data set from this year. Shannon Hawaii was good enough to give us this. Typical data set, a little bit of survey just south of Puerto Rico, and then a big long transit in. We use just a subset of this just to keep the times down, because time is money in the cloud. But a real data set, not a toy data set. And we did 3 configurations. So we did 2 in the cloud and 1 in the local. Now, don't worry about the details of it, but just if you haven't seen these before, or if you don't do this on the as a regular process, these are pretty big iron. These are big enough iron that I had to get special permission from Amazon just to turn them on. A standard account, you can't turn these on, just won't let you do it. Because we asked for a lot of CPUs and a big chunk of memory, and particularly a GPU physically attached to the device. Cloud doesn't really like that very much. GPUs for machine learning, yeah, they're all over that. GPUs for actual graphics, not so much. Now, we don't actually use the GPU for much in what we've done. But desktop software is so used to assuming that it's there, that their software is like this. And their data processing, their graphics processing are intrinsically linked to each other, so much so that this software that we're using won't even start if it can't find a GPU, or at least get a graphics context. So we're stuck with what we do. Now, if you can see, they're expensive. $1 an hour, $1.75 an hour. And that quickly adds up. Now, look at the performance. Variety of ways we could look at this. We actually looked at data conversion and processing. This is just for making grids, just by way of example. The blue here and the green here are 2 different cloud implementations. The black here is the local. And there are 2 examples, one to the left of the line and one to the right of the line, 2 different versions of the grid that we're generating. Clearly, there are winners and losers among the storage technologies, which is what's along the horizontal axis here. There are some that are much slower than others. So we learned a lot about that. The key issue here is that the performance on the local is dramatically better than the performance in the cloud, even for what should be about the same sort of level of performance in the cloud. Because it's tightly coupled, and because I think we're getting a lot of advantage from caching here, which you just don't get in the cloud because you're sharing it. Now, here's the kicker. I'm still working on the absolute numbers, but by order of magnitude, if we say that processing a data set takes about 90 days, I mean, we don't often get there, but that's kind of our goal. I could approximately buy a new desktop machine for every survey I process and still be better off in terms of the costs involved. Because of the way the licenses work, we can't turn these off without actively managing the licenses. If you turn one off without managing the license gets invalidated and you have to have the manufacturer turn it back on again for you. So you need to run either that, either you do that, or if you leave it on all the time, or you run a second server, the costs quickly add up. Economically, I don't think it makes an awful lot of sense. Here's what I think we should be doing instead, and this is what we've been working on with a couple of colleagues here at the university and with Eric Youngkin and HSTV. I promise we're not using too much of Eric's time, it's just very little. So we're not really allowed to. What I'm suggesting that we do is go by that mantra: if the data goes into the cloud, the processing must follow. And we build in the cloud everything we need to do the processing. We have a compute engine here, and its job is to maintain a current estimate of depth. We tie it directly to the data storage, and we say we want this guy here to be giving updates of depth at a regular interval, say once every 10th of a second. And if the current compute load that we have is bigger than that, we add more compute here and actually take advantage of being in the cloud, which those desktop systems cannot do because they're designed to be on a physical device. We tie a network interface to it and we do the visualization outside where the GPUs are cheap. And we have to be very careful about how we manage that, but I think we have a solution. Actually, Tom Vukovic, there's Tom. Tom's here right at the back. Tom's going to talk about it in the next talk and exactly how I think he thinks we can do it, which I very much approve of. We don't want to build the whole thing ourselves, so we've worked with Eric to use Cluster as the kind of core engine in here. Now, Cluster is a really interesting project, all built in Python. It's designed to use technologies that scale really well. It's designed, however, primarily to work on a desktop. It's tested mostly working on a desktop. And so what we've done is we've built it into a Docker container, to which we then running in a Docker host, so we can do multiple of them, to which we then attached a network interface to proxy the commands into the Docker container for us, and a command interface so we can actually control them. Having done this and having it talking to the hostess to get data back and forward, we can do multiple of these and scale them up and scale them down, give us more or less compute power, and still talk to it over the network. Essentially, we can deploy this in the cloud with something like Kubernetes or ECS to do the management piece for us, so we don't have to pay for the management piece as well. Well, we pay money for the management piece, but we don't pay time to develop it. That's what I mean. So we have that working. We're doing performance tests on that right now. What we're also doing, though, is building out that infrastructure to do this implementation in the cloud to prototype and demonstrate how this processing would work. So what we've been doing recently is building out this, which looks like that in our current model. I love these diagrams. Everybody else was going to show the diagram. Roughly what it is, data goes left, right, and here. Time series processing happens in this column. Spatial processing happens in this column. Well, it's come out the right-hand side here. The key issue, though, is the boundary in the cloud is here. The users are outside. But it's designed so that you have one spatial processor per data set, but any number of users can attach to that data set using the dataset broker service, so that you can have multiple users working on the same data at the same time without having to pre-process your data, break it up into chunks and separate it out and do all sorts of controls. So you could have multiple users processing the same data, or a couple processing and a couple doing QC all at the same time, simultaneously in the same environment. Think about Google Docs for your Bathy data, where you have multiple people simultaneously editing the same document. That's the goal that we're looking for. And if I have my way, these interfaces here will be VR goggles and data sets, which is what Tom will show you just in a second. We don't know whether these are different or the same thing. We're working on that now. We're working on how we build this out so that we can scale up and scale down these environments to give us that real-time guarantee of compute. Hopefully, by the time you come back next year, and we're also here, we'll have something to demonstrate for this one, probably at that time. Thank you.